So we're going to overview a computer system. Okay, there are many basic computing concepts that are not related to distributed computing, that are relevant for distributed computing, and I kind of assumed them last time, or didn't give you, very detailed explanations or hand waved. So we'll go through these basic concepts, and I might insult your intelligence. You guys might know this all very well, but use this as an opportunity to make your own definitions of these terms. And let's just start from the basics. Computer, bus, CPU, device readiness. So who knows what device readiness means right now? Let's talk of computer bus, CPU, and device. So what's a computer bus? Anybody want to describe? And we're going to do a very superficial overview here, right? I mean, there are whole courses on this. So computer bus, yeah.
Usually like communication between two pieces of hardware that communicate on a bus.
Between two independent pieces of hardware that you can, plug and play. Okay, so and the pieces of hardware might be, examples might be?
USB
and sorry? Processor, okay. So it's often the processor is kind of the mediator. Processor and USB, processor and keyboard, processor and display, okay. So CPU is the processor. So how would you, and there's devices also. So we talked of processor and USB. So somehow the processor is different. So what's the difference between a CPU and a device? And CPU being a processor. They're all processors of some kind.
The CPU does the actual computation, the device feeds it the information that the processor needs to do.
Okay, so CPU is like the master. It does the computation, or it does any computation. It's general purpose. Device is feeding it information, and there may be multiple devices, and they all.
Like a disk is just meant for storage. The CPU will hold the disk to do different.
So there might be so examples of devices are disks, and they all have their own idiosyncrasies. CPU, we know, is something that's standard. It's supposed to do general purpose operations. Okay. So does the CPU have any data inside it? Registers, cache. Does the device have any data in it? It's feeding it information. Or it may be receiving information too, right? So that information has to reside somewhere. Okay? So how does the CPU get hold of the information in the device? Through the bus? Or it can go and do direct memory access. So memory is yet another thing connected to the bus. Okay. So so computer bus allows CPUs and devices to communicate and access memory. Okay. CPU interprets general purpose commands, and the commands are in instruction registers. It decodes these registers, and it then has other registers into which it performs computations. And you can load them into memory, and you can save them into memory and load memory into registers. And device from some special purpose computation. There's so many kinds of devices, right? Also has registers. We'll call them device registers, and accessible with the CPU through the bus. And as it turns out, the device registers are associated with memory addresses. So some memory addresses refer to real memory. Other memory addresses refer to device registers. Okay, different device registers are different memory addresses. So the CPU just goes and says, I want information on this memory address, from this memory address, and either the memory feeds that data or we get it from the device. Okay? And what's a real-time clock? So the other devices you might, keyboard, display, network. The real-time clock is a very important device.
Like the onboard clock?
So there's a CPU clock, right? That's just making sure that, okay, the next instruction comes at the next clock cycle. What's an external device clock doing? What's its job? Yeah. So time of day is something I can read. Okay, so time of day might be a device that I can just read anytime. So there's time of day clock, there is the CPU clock, yeah.
It's synchronizing access so that you know when data's going to be ready. And
So that when data are going to be ready is when the data get ready. It's not happening at a certain time. So the CPU clock is the clock that determines when you determine a CPU, when it goes and actually determines whether the data are ready or not. On every clock cycle, or at least hardware might have changed since I studied it, but there's the cycle stealing that after every clock, CPU clock unit, you go and check if there's any data ready. So there's time of day clock, there is time of day, there's the internal CPU clock, and there's also a device real-time clock.
Is that for a real-time system?
For real-time systems, because
It's required to complete certain tasks at a deadline.
at a certain deadline. So the operating system has to keep track of time passing, right? And real-time computing requires that. But just an ordinary, boring operating system that schedules threads, does it need a real-time clock? You want to switch between threads, among threads. So your context switching among threads occurs because there's a real-time clock. Okay? So it counts how many units have passed since you got scheduled last time. And it says, oh, you executed too long, so it's time for somebody else. Okay? So now let's talk about device readiness. What does device readiness mean? So what is it? And we've talked about that last time. Let's just be a little bit more explicit. So my keyboard device, it's ready when? No, interrupt is sort of an indication, a signaling of readiness. We'll come to that later. So, ready for what? Keyboard device is ready for what kind of access from the CPU? Read. So the CPU clock, the keyboard device is a producer. The CPU is a consumer. And it's saying, my device register is non-empty, right? It's got something you can read from. Let's assume there's just one piece of information that is there. It's not a queue. It's saying that memory has got some information that's of interest to you. It's not just like ordinary memory. Memory is passive. A device's memory is active. I mean, data get put into it, and sometimes if you looked at the data already, then it's not looked at again, and you're interested in the next piece of data that arrived. So it's something that's either a producer or a consumer, or is generating clock interrupts, which is also sort of a producer of information. And a display device is ready when it is. So the display device, the keyboard device is a producer, the display device is a? So it's ready when?
there's a new friend control.
Or if we just consider this to be a character output, just assume for a moment, the good old days. Its device register is being consumed. So its data are non-full. Okay? So non-empty and non-full are two important kinds of information. Okay? So it's basically saying, it puts a bit on saying, okay, now this data, you can write into this, or you should read from this now. Okay? The CPU can poll this data. You don't need any interrupts. In fact, if you're writing interrupt handlers, you want to debug the interrupt handlers, right? How do you debug the interrupt handlers without, because for debugging output handlers, you need to print out things. So when you're building an operating system, you're implementing printf, but you need printf to debug printf. So we had kprintf, kernel printf. That's a polling kind of thing. It just keeps polling to see whether the ready bit is on or not, and whenever it's on, it goes and prints a character. And that you can use to debug the print interrupt routines. Okay? So you don't need interrupt routines to really interact with devices. Okay? So, and all this is going to be relevant. This is synchronization. Distributed computing is going to be a lot about synchronization. Let's look at the most primitive form of synchronization that the hardware gives us, and that will inform the kind of synchronization we'll have in software layers too. Okay, and it'll be good to go and relate those to this kind of synchronization so that you have a very holistic view of the whole system. Okay? Questions so far? Okay. Bunch of more terms. So you've written Java programs. In 4.11, you've written C programs. Some of you have written Python programs. So let's abstract out and sort of describe what a program really is. And, again, it's not for first principles, but something that unites all these languages together. So if I was to tell you what's a program, define a program, what would you say? Set of instructions. Okay. Just instructions. So there's data and instructions. Okay. And you can divide the instructions into some form of units. So it's just not one linear sequence of instructions, right? So you'll divide them into, in Java you'll call these methods, in C you'll call them functions, procedures, okay? So, okay, good. We know what a program is. Process.
Program along with its state and its memory context.
So a program along with its state and memory concepts. So you're saying the instructions of the program plus, so when the program was declared, you just said what kind of data you want. There was no data allocated in memory. You said, when I'm executed, I want these data, right? So a program, we'll say, is a bunch of procedures with local variables, okay, plus some global variables, and there's a distinguished main procedure. Okay, if you're going to have a bunch of procedures, we want to know what a distinguished procedure is, and that's called the main function in C or the main method in Java. Okay, some entry point, and that's just static. It's just a script, it's just a book, and a process is some actor reading the book, okay, or performing the script. And so that's a process. And I said, okay, so you've got a program and you've got an actor that's performing the script. And is this a single actor play or a multi-actor play? So it's multi-actor if it's what kind of program? Multi-threaded. Okay. So we have one common script. Okay. And we have this multiple threads that can execute it. So how are threads created? We know that if there's a main method or a main point, and when we execute the program starts executing at the start of the main method. And this is all a linear sequence, so we go to the next instruction and so forth, and we jump when we need to, when we come back from the jumps when we need to. So we know what the starting point is, and after that we know from our assembly language programming in 4.11 how control goes. Okay, or our understanding of Java, we know that once we start something, we know how it flows. So we know how to start the main thread. The main thread is basically the main method and all the methods it calls. Okay? And when a main method calls another method, does the main method keep executing, or does it stop while the other method is executing? Stops and waits for result back, right? And that result sent back to you through the stack. Okay, so a thread is like a stack. A thread is defined by a stack, essentially. How do we create new threads? So what you can do is you can create a copy of a program that's running already and say just continue on here. The program is so you're copying the address space also? You're copying the memory also?
They have a shared memory space.
Sorry?
You share the memory context between different threads in one place.
So if it's if it's so, there were two answers here. So if it's a thread, you share the memory, right? So do you agree that you're copying whatever's happening right now? You make a copy of it, like the main method. You make a copy of the. Okay.
No. This is the separate process.
So when you create a process, another process, you do a fork, and there's a v fork and a fork, depending on whether you're going to share the code segment, memory segment or not. Okay, but let's not get into that. So let's talk of threads. So I've got a Java program, let's say I start with the main method, that's a thread. How do other threads get created? Conceptually what happens? I don't know the API, but what's really happening? So a thread is created by the OS. The first thread was created by somebody else. The other threads are created by own code or by somebody else. Yeah.
It's created by like the other thread, right?
So the existing threads create new threads. Okay. Actually, some threads are still, there are threads that are not created by us, but created by JVM and Java. So a thread can fork or spawn another thread. Okay. So you can talk of parent thread and child thread. You don't talk of parent procedure and child procedure because it's just part of you. You did this and you're coming back. You're stopping. Whereas now you've got so you've got, like you said, multiple actors. That means multiple actors can act at the same time. So there's some kind of concurrency we're talking, right? So multiple threads can execute concurrently. They'll probably interleave on a single CPU, and one thread can fork another thread. So there's a child thread, and the child thread now is autonomous. So does if the parent thread dies, does the child thread also die? Independent. The parent started it off. Parent doesn't wait for it. So basically, can you think of a thread creation being a special kind of procedure call? What kind?
You just can't wait for it to return.
You don't wait for it to return. It's a non-blocking call. A procedure call is a blocking call. Use same stack. This is a non-blocking call. You say create a new stack, please. And that stack will exist as long as that root procedure that you called doesn't return. So you can think of each thread being a non-blocking execution of a root procedure, not a function. They better not return a value because nobody's waiting for the value. Okay? So it's just a procedure call that doesn't return any value. You get back a thread object. And what can you do with the thread object? When you create a thread, you can get a thread object value. That's not the return value of the root procedure. Okay? And and you OS guys sort of will be able to answer this question better, but those who haven't done OS, what might we do with what we get back from a thread? What operations might we want to perform on a thread? OS guys?
Figure out when it's finished.
Sorry?
Figure out when it's finished. Like find out when it's finished.
Okay, wait for it to finish. You can join it. What else? Yeah.
Synchronize it with other
Synchronize it with other
threads.
threads. What would that really mean?
Like waiting for other threads to reach the same point.
So that would be an operation performed by a thread on an object like a barrier, or would it be? So I can understand waiting for it to finish. Okay, because you can sort of say, I want to wait. Even though the thread, so this is interesting. We're going to see this in non-blocking I/O. Non-blocking I/O doesn't mean we never wait. It means we don't wait in a very specific way. So I can create a thread, I can do my own work for a while. I say, now I'm done, but I need to know what the thread did. I may be multiplying two matrices. Okay, so I multiplied my row, and now I'm waiting for my thread to multiply, my child threads to finish multiplying their rows and columns also. So then I join and I go and wait for all the children threads. So it was non-blocking creation, but I blocked later. Okay, synchronizing is done sort of at the method level, at the object level, not sort of at the thread level. Because what would it mean? It just have a thread ID. Right? But other operations, if a thread's gone amok, what might you want to do to it? Okay. If a thread's not getting too much CPU, what might you do to it? Sorry, shred it.
Suspend it?
Suspend it. Very good.
Give lower priority.
Change its priority. Okay. So there are these thread operations. So you do get back something from a thread object when you make a thread call. It's not the return value. Okay. So thread, execution of a method called chain, okay? That means it's got a stack. We're creating a new stack, has its own stack, okay? Concurrent or interleaved execution of threads possible. If we are lucky and have lots of processors, it's concurrent. And they can start children threads and terminate before the descendants, okay? So the parent thread. So a lot of the GUI programs you guys write, the main method finishes, but the program doesn't terminate because the GUI thread is running. Every time you create a frame, the GUI thread is okay? Your distributed program, the server main method will finish. That doesn't mean that it's gone. Okay, it's gone and said, I'm waiting to listen to events, and there are some threads created as a result. And so it's listening for the messages. Okay, so main thread is very easy. Thread that executes the main method started when the program is executed. So no API is required for this. For other threads, some API is needed to go and say, make this call asynchronous. Okay, and there might be different APIs. We'll talk about a command object at some point. Okay, process represents an executing program. Okay, so a piece of memory, an address space. Okay, an address space has a code segment, okay, where the instructions are, data segment, and it's got all this heap, you know, and it's got a stack segment also. So there's the main memory, there's dynamically allocated memory. Dynamically allocated memory includes stack and heap. Okay, heap is, you guys study heap in data structures, you must study heap, right? Mm-hmm. And the heap is where your dynamic point, you know, whenever you allocate an object, that's the pointer that object comes from. Okay. So a process is confined to its address space. So we have a shared memory, and then memory is divided into multiple address spaces, and there is some access control. Okay, this access control is going to be important. Okay. So address space, and access control means that, you know, two processes can share things. They can share data, they can share code for sure. They should share code if the code is not being changed dynamically. Okay. And of course, you know, stacks and heaps. Okay, I should have also mentioned heap here. Okay, so what does and now the OS guys know this answer better. So how about some non-OS guys for a minute? What intuitively, what does atomic execution mean to you?
Either an operation fails or, well, it'll succeed or fail. There's no between. You can't do any of the partial steps.
Okay, fantastic. So that is a database definition. Okay, and there are these properties called ACID: atomicity, consistency, isolation, duration. And it has to do with failure. Often has to do with writing information on disk or some kind of stable storage actually. And you're saying either the operation has finished completely and is durable, or it didn't even finish. So you can't go and say I did these two stop steps and I started this lecture, I didn't finish it. Either I finished the lecture or it's as if I never did the lecture. Right? From a concurrency point of view, what does it mean? Yeah.
It means that, like, two threads are accessing a shared resource and one performs an atomic operation, one thread can interrupt the other one.
So when you're accessing some shared memory and you're doing some computation in the shared memory, your results cannot be influenced by some other process threads. Okay? So that's atomic. And that's, you know, I mean, if you have two actors and they both want the mic, okay, we need synchronization. Okay? So atomic execution is extremely important. And okay, so there is some critical region in shared memory. Actually, critical region often is referred to by a set of instructions. So just think of there being some data type, data that two threads are accessing, and we want the accesses to we want to make it appear as if there's isolation. There may not be real isolation. We want to make it appear as if no other thread accessed it, or at least influence your computation. So whenever there's some shared data structure and some thread starts manipulating it, there's a notion of an invariant. You guys heard the term invariant? You've heard invariance in terms of loop invariance, right? Have you heard invariant in terms of data type invariant? In OS, what with monitors, you guys
Yeah.
study
Yeah.
invariants? So whenever you enter a monitor, you want to maintain the invariant. Whenever you enter into some object, which is called a monitor, you want to make sure there's certain relationships among its variables. So you might change the variables, but certain relationships you want to be true. Okay, if you go to Q, okay, which is doubly linked, you can't have one link and not the other link. Okay, it's either got to be linked, doubly linked, or not linked at all. Okay, or basically it's only got to be doubly linked, and if you're inserting a new item, it better be doubly linked before you end. Before you end doing that. Okay, so atomic execution is extremely important, and again very relevant to current computing and hence distributed. Okay. No buzzwords here. Everybody understand? Okay. Okay. So lots of people came to me and said, "What's a kernel?" Okay, and idea of kernel is related to OS. So why do we need an OS? You know, OS is something you didn't write, right? So why don't we just call it a bunch of library routines? Is the OS just a set of library code that's just written? Or is there something very distinct about this piece of given software that distinguishes it from other software that you might use?
So all your code is sort of running at one level above the OS.
So you are layered on top of the OS.
Right.
In some sense, you're layered above. If you're writing in Java, you're layered above Java also, right?
Above the JVM.
Yeah. So you're layered. Well, also the Java abstractions, right? Often the Java abstractions just present the OS abstractions. So layering is something we do to beautify some ugly things underneath. The ugly thing underneath here is the hardware, right? Call it ugly, or you can call it primitive. I mean, it's skinny at least, so it may not be that ugly. Operating systems are bloated, so they may be ugly in that sense. But somehow you didn't want the skinny skeleton, and you wanted something more sophisticated. That's more in tune with what you want to do. Okay? So what distinguishes a compiler or a database from an OS? They're all layers that you build on top.
The operating system is what manages resource access at the end of the day.
So it manages accesses of shared resources.
Yes.
Shared among whom?
Among user level processes.
Among processes, user level processes, or there may be other kinds of processes. That's interesting. So it's a mediator. Okay, when I say it's a policeman. Okay, other software are not policemen. This is a policeman making sure that you're confined to your own home, your address space, or whatever you've been authorized to access. So because of the authorization, because of access control, we need protection, we need operating system. Okay? So how do we ensure that's, so we know that some software engineer built the OS also, right? How do we prevent some arbitrary program, some virus or your own program to just become the OS on a computer? How do we make sure that only some software can be considered OS and not other?
We use some kind of kernel or using
So you probably need some support from the hardware. The hardware is designed to be beautified. The hardware says, I have two modes. Actually, they can be rings. There are multiple rings. And there's a system called Multics, which came before Unix. the word Unix is a play on Multics, and Multics had 64 rings. Okay, the PC at one time had 4 rings. I don't know how many more rings it has now, but basically they're levels. Ring means the kernel mode and user mode, and kernel mode is more powerful than user mode. So the inner, more inner. So the more inside you are in the ring structure, the more power you have. Okay? So more inside you are. Okay. So we need a kernel mode in the hardware saying, I am now executing in the kernel mode. I can do special things. Okay. And in this mode, and in the other mode, I can only do what users can do. Okay? So we have, okay, so what is the difference between a kernel and an OS then? Yeah.
Is the kernel like the manifestation of the OS or the way that it interacts with things like actually operates?
So you're saying OS is a piece of code and kernel is the execution of the code.
Yeah.
Well, that's one definition. Not quite, but that's, if you don't know the difference, that's a good creative definition. Yeah.
Kernel, like the kernel is protected and has direct access to hardware and shared resources. The OS manages when you can when the kernel can be used to access such things.
So you're saying the kernel is the one that manages resources,
Directly manages.
and the OS does it indirectly through the kernel?
Yeah, by triggering a kernel node, by triggering a syscall and going into.
By going inside the kernel. Yeah, go ahead.
Isn't the kernel a part of the OS that's always running and it can run other OS features outside of the kernel?
So if you look at the word kernel from English, it seems to be the inside of a nut, right? The inside part of something, right? So it's the heart of the OS. That's intuitively what it is. Okay, so the OS is layered on top of the kernel. Okay? And it was mentioned earlier that processes that run in user mode, they can be processes that run in, they can be user processes and they can be operating system processes. And when we talk about distributed operating system, we're often talking about processes running in user mode, okay, that do operating system functionality, okay, that provide you with abstraction, that manage resources, and now the clients don't make kernel calls, they make service requests to the processes saying, please do this for me, please open this file for me, please close this file for me. So they're not making a call to the kernel, they're sending a message to a server that is doing operating system functionality. Okay? So think of an OS as being kernel plus a bunch of OS servers. Okay? And the file system is a very good example. File system is something that takes a lot of coding and it takes a lot of memory, and people have wanted again and again to remove it from the kernel. And they've done it many times. And then performance goes down because you're not making a kernel call, you're sending a message passing is slow. Okay, and so it's being like fashion, they keep going in and out of the kernel. But that's one thing that's not inside the kernel. Now, what do you think of the shell program that you guys have used in 4.11? You guys used at least shell in 4.11? Would you consider that part of the operating system? It's a user level program, but it is the user interface of the operating system. In Multics, it's part of the kernel. Okay? Hardwired. In Unix, got taken out. Okay? But that's something that people have taken out and has remained out. Okay? The file system has sort of, you might have heard of microkernel systems. They are very small kernels, and most of the work is done in servers. Okay? So there's a distinction between kernel and operating system, which we won't get into too much. But the kernel is the piece of code that runs in kernel mode. Okay, it's always resident, as you hinted. It's the piece of code that also runs in the kernel. Okay. So, what is? I like to use the word trap. You guys heard the term trap anywhere before? And it's often also called software interrupt, which I like to use for something else. So what's a trap? What's an example of a trap? Yeah.
If you make some type of system call from user mode, like read or write or something like that, then that will cause the trap.
So here you're trying to do something good, okay, like make call put on the key or call get on the keyboard. So that is something that's going to be serviced by the operating system, by the kernel. Okay, it involves ultimately accessing some kernel data structures and some device registers finally. So how do you go from user mode to kernel mode? You execute a hardware instruction called trap. That instruction takes an argument saying what kind of trap. Okay? There are many kinds of traps. And there's a system call trap which takes as an argument which system call. And associated with that system call is some piece of code, and that piece of code starts executing. So that's how you go from user mode to kernel mode. Okay? It's not as if once you start the user mode, you never go back to kernel mode. Okay? And how do you go from kernel mode to user mode?
Context switch.
So how do you do the context switch? Switch often means changing context.
Return whatever call is brought into the kernel.
Sorry?
You return whatever call is brought into the kernel.
So you have a special hardware instruction. Just as you had a hardware instruction that said execute the trap instruction for system calls, now you have a return from trap instruction. Okay, that turns you back. And now this is an expensive call. Jumping to some piece of making a procedure call is relatively cheap. You've got to allocate some memory on the stack. You know, that's got some overhead. Okay, but now you've got to go into a different stack or different area of the stack. Now the stack is a region in kernel memory. Okay, and so that's expensive. And that's a good trap. There's some bad traps also. Have you guys heard of traps in some? When I say bad, I mean not what you expected.
So, segmentation calls?
Some kind of fault. Okay, segmentation fault or arithmetic overflow. So a trap handler is executed in that case. So there are many kinds of traps. Okay, segmentation fault may be one, arithmetic overflow may be one, or make a system call trap. Okay? And then make a system call trap has some argument to it that tells you which system call. Okay, so you can have only so many different kinds of system calls. Okay. So OS creates processes in their threads. Okay, the abstraction of a process is defined by the OS. In fact, by the kernel. Okay, because if the operating system is kernel plus server processes, who created the server processes? The kernel. Okay. It's the device registers that I talked about. That's a shared resource. Okay, who should read them? There's many different threads that you want to read them, so somebody has to mediate the access, okay, and determine whether the access is even allowed, especially if it's a file, okay. So it basically beautifies the hardware and mediates resources. That's what. And the resources are not just hardware resources, okay. It does mediate the disk and the keyboard, but it also defines resources like files. Files are defined by the operating system. They're not defined by the hardware. So it defines this abstraction of a file and then mediates access to it. Okay. And in the distributed computing world, it defines the notion of ports, and then decides who can access what port. Okay. So the kernel is portion of OS that executes in kernel mode is always resident. Okay. Kernel mode is a mode in which you can access all of them. Assuming there's only two modes, kernel mode and user mode. Like I said, there can be multiple levels there, always. Okay? And user mode is the mode in which you execute, which your access is limited to a processor address space. Okay? So what happens is that there's a trap handler, okay, that's executed depending on the trap. And that handler executes in kernel mode. So and it might be a system call or an error handler. Okay, it's a trap handler that executes a system call such as get or put. Okay. Lots of text. I just put the text in there because for you guys to read later. And again, this is not being thorough. It's just giving you enough background so that what I say doesn't become just buzzwords. Okay. Questions? Okay. So now we're getting into a little bit more specialized OS knowledge. But hopefully, even the non-OS guys can make sense of some of this. So let's talk about thread switch, right? Thread switch would mean what, intuitively? Between two threads. And process switch is switching between threads of two different processes. Thread switch is switching between threads of the same process. And which is going to be more expensive? In one case you got to sort of change the address space also, in one case you don't. Okay, current ready block thread, that's something even as a user of threads you should be able to understand. So the difference between a ready thread and a block thread, non-OS guys. Okay, current thread and a ready thread.
Current thread is a thread that's running and it's being executed.
And ready is some.
It's on the ready queue.
It can execute.
It can be executed.
So when you do a thread switch, you switch to a ready thread. And what was current becomes ready, and what was ready becomes current. Right? Okay? And block thread is a thread that?
Can't execute. It's on the blocked queue.
So if I'm doing a get and there's nothing to get, I'm blocked. So a thread is blocked. Okay, that means what? It was running on the CPU and said, what happened now? Somebody else has a CPU. But here was a thread, it had registers, it had a program counter, it had a stack pointer. What happened to that stack pointer, the program counter, when it's blocked or when it's not current?
It gets saved.
It gets saved somewhere in memory,
Yeah.
in kernel memory. And that piece of memory is called
The thread control block.
a what block?
Thread control block.
Thread control block, context block. Okay? So that's a process table entry, context block. So that is a piece. So a thread is something you think of as a very active thing, right? It's an actor, but it's actually data structure. It's a data structure called the context block. That's what the thread is. Okay? And the context block has a pointer. It's only when it's executing, when it's running, that it becomes active. Okay? So the thread context block is a data structure, the object that represents a thread, and the process context block is the object that represents a process. Okay? And they're all objects. They're all pieces of memory. Stack pointer, program counter, other registers. So basically, whatever the registers were of the particular process, they get saved in memory, and then they get loaded when the thread becomes running. Okay? Okay, so again, this is area in the kernel memory that represents a process address. I don't know why I say portion of OS. I should correct that. And so it's got the address space, it's got what threads it has. Okay, the thread has got what stack it has. And thread switch, giving a CPU to another thread of the same process. Process switch, giving a CPU to another thread of a different process. So when threads are in ready, when they're ready or when they're blocked, they're in queues. Right? Because there may be three different threads that are waiting for the input. One came before the other. Okay, there may be three different threads that are ready but not executed. So queues which you guys have studied in data structures become a very important abstraction in operating systems.
Are threads and processes scheduled on the same queue when the OS is still running?
So there is thread scheduling and process scheduling, right? Thread scheduling says, assuming I've decided to go in favor of this process, which thread should I use? And process scheduling says, which, should I be executing Word right now or PowerPoint? Okay? And you can probably come up with a zillion strategies on how to schedule things, whether it should be just a flat level scheduling or hierarchical scheduling, where you first decide the process, then the thread. And so, yes, you can have a process queue also, in addition to a thread, which just decides which is the next process. If you guys are interested, I've actually got some interesting material that I've created on multiprocessor scheduling and what happens multiprocessor scheduling. But that becomes a little too OS-ish. We don't really need that for distributed computing. This stuff I was referring to already in my first lecture, so I'm talking about it. So you can imagine a multi-level scheduling.
Are the thread queues stored in the PCB for their respective process?
So PCBs are the entries in the queues. It's a queue of PCBs. When I talk about a ready queue, I'm basically saying this is a queue of each thread is associated with an ID. And when you go and create a bunch of queue threads, you're linking some objects, right? What are the objects linked? They are the PCBs. So yes, a PCB might have a next pointer saying that's the next element. To that extent, it is involved in queue management. But the queue is a separate data structure that's uniting together a bunch of context blocks. And a context block is only one queue at one time. Because which thread's queue will you put the ready queue in? Right? The ready queue is a separate data structure.
No, I'm saying if you have threads for like a respective process.
Ah.
Are the threads
Sorry. I didn't get that. So you're saying the storage might be hierarchical, right?
Yeah.
Sure. Or it might not. Sure, and that's the representation. As long as the thread has a handle to the process, we know how to go from the thread to the process to the thread, and now we can further go into that. Context switch. We know what a thread switch is, what a process switch is. What's a context switch? That's a process switch. It's just switching from between kernel and user. If you go and do a put, even if you didn't do a block, don't block, you've gone and done a context switch, which is expensive. Okay? But typically what schedulers do is they say, we know context switches are expensive. Now that you have come into the kernel, let's go and switch you out and put down the thread there. Because pretty soon you might be doing, your time quantum might be over. So let's just, why wait for another system call, let's do another context switch. So a thread switch, if the thread is supported by the kernel, some threads can be supported by libraries also. If the threads are supported by the kernel, then a thread switch implies context switch. Context switch by itself doesn't imply a thread switch, but in practice often results in a thread switch. Okay. Switching from user to kernel mode, or vice versa. Okay. And often results in thread switch. Okay. So one more buzzword taken care of. We haven't even talked about interrupts. Okay. So what's an interrupt then?
What happens in the context switch?
So when you do a context switch, you're doing a trap.
Yeah.
And that's, some people call it software interrupt. I don't like the term software interrupt. So, and when you actually do a trap handler gets executed. So interprocessing must be similar in some ways. Otherwise, why would you call a trap a software interrupt? But what's the difference?
The user can generate them.
In which case can the user generate them?
I believe the user can generate an interrupt.
How does user interrupt?
Like if you're typing on your keyboard.
Okay, so the device happens to be a keyboard device,
Yeah.
then the user generated. So you know, when you're an OS person, you don't know what the user is. We talk of the end user, and then we also talk of the application programmer. So when the application programmer makes a system call, in that case the user, the application programmer generated the event because they executed system call. But yes, a device can, so now an external device is involved. Trap is within the CPU. You're executing an instruction in the CPU and you decided to go to a trap handler. Now an external hardware unit is involved and it says, I want attention. And how does it get attention? By posting an interrupt. What happens when you post an interrupt?
There's an interrupt table.
Just as the trap number is associated with the trap handler, an interrupt number is associated with the interrupt handler, and you start executing the interrupt handler in what mode?
Kernel mode.
It's a distinguished thing, the kernel. Okay. And the device will interrupt when it is? What events cause it to generate interrupts? Whenever it goes from non-ready to ready state. Whatever that means for the device. It's saying, I just got ready. And it won't, once the interrupt is serviced, it won't again post that. It remains ready, it won't say that. It's only the transition from non-ready to ready. Okay? It's this whole thing when you guys study producer consumer problem, when you suddenly become from empty to non-empty, or from full to non-full. Okay? So when you enable or disable interrupt posting, what are you doing?
You keep the device from making an error.
You prevent the device from saying, don't raise your hand, please. Okay? And when you are enabling, disabling CPU interrupt process servicing, what are you doing?
The CPU just ignores the errors.
You're just saying, I know, please keep your hands up. I'll come to you. But right now, I'm just thinking, I don't want to. Okay. So, what happens when there are multiple CPUs?
You have to have something to route the interrupts to wherever the program is running.
So the question is, the interrupt servicing happens when an interrupt routine executes on some processor. Which processor? So, who knows? Okay. When I was studying this stuff, or when it posts to everybody, and some processor decides to. So I Googled today to see how outdated I am, and I tried to find the answer, and all I got was a bunch of papers, which means that this is something that people haven't figured out quite. Okay? But from what I understood is that it's chaotic when any processor can service an interrupt, because then you can have one processor executing an interrupt routine, another processor executing another interrupt routine, both in the kernel, both accessing the same context block, or accessing the same ready queue, and we don't have atomic execution. So it's sometimes a designated CPU. It's always maybe CPU 0, or with each device you can say this is your CPU. Okay? So there's something to worry about. Okay. So enabling, disabling device interrupt posting, instruction asking a device to post, not post a signal to the bus indicating it is ready. Okay. So the whole idea of interrupt processing is that you don't have to poll the ready bit. You don't have to rely on kprintf. You can just have a printf that's interrupt based. Okay. So execution in kernel mode of a handler by the CPU that services the interrupt, handler indexed by interrupting device. Okay. And the question is, what thread is executing when the interrupt routine executes? And this is where you get into all kinds of answers. Some kernels have kernel threads in them. Okay. Some kernels don't. That means there was some user thread that was executing, and suddenly an interrupt occurs, and that thread stack is used to service that interrupt. So it is that particular thread. Okay. And interrupts can be directed to a special CPU, designated CPU, or any CPU with only one of them servicing it. Okay. And enabling, disabling CPU processing. So it's an instruction you execute, and you go and say, I don't want to. The devices can be put in a hierarchy, and you can say, I don't want to listen to any device that's lower than this number, or you can say all devices. Okay. And so how much of this was covered in 411? No? What do you guys do in 411? Assembly language programming and some C programming? No, it's fine. Everything, all of that's all good stuff. I'm just curious. This is how I learned what happens.
More hardware stuff,
Like what?
like
ALU?
ALUs with multiplexes and whatnot.
Do you mean operating systems or the organization?
I mean, I know you don't trust what my knowledge of numbers, which is correct. But yes, and I didn't mean what was called 120 at one time, which is the. I did mean 411.
Yeah, most of this was like robot stuff.
Yeah, and I mean, this is So I feel you shouldn't graduate without compilers and operating systems, okay? Personally, because you go tomorrow to a job and people are going to talk this language, and it's important to know this stuff. So it's more important to know this stuff than ALUs, even though I'm a double E major. Okay, so I went up to transistors and I went up the stack. Okay? But it's good. Okay, let's go to data structures. So when you guys did your queue implementation, did you do linked list, arrays, or both? So let's talk about array queue. What happens in an array-based queue when the array gets full? What did you guys do? Did you? Did you guys do that? Allocate a new array? You could.
Yeah.
Or what is the lazy approach?
Circle back.
Sorry?
What is a queue? Sometimes you create a circular queue, circle back.
Oh, but circular queue, you did OS, right?
Yeah.
No, but that circular queue makes sense only in OS. It doesn't make a sense because as long as you, okay, what you're saying is that to save copy. Okay, sure. But even a circular queue can be full. Okay? So circular queue, so what happened when the queue got full? What does Java give you as an abstraction to do when something bad happens? Throw an exception, right? So linked list, well, when the whole memory gets full, you do that. So what's the difference between a bounded buffer and a circular queue? And a regular queue? What happens when the queue gets full in the OS world?
You don't write anymore.
You just block.
Yeah.
You didn't block in the first case. You blocked in the second case. You threw an exception when there was only one thread, saying you've got too much to queue. Here you're saying, that's okay, you're queuing up, but there's somebody else who's emptying it too. So there is hope. At some point you'll get unblocked. So it's a queue that's accessed by multiple threads. And that's where it becomes active. And one thread's producing, one thread's consuming, or maybe the same thread, but sometimes consume and sometimes produce. But the point is that the queue is, there's multiple threads. Okay? And that's when the circular, and this is where you have a circular queue that you wait on. Yeah. Okay? So full queue during enqueuing and empty queue on dequeuing is an error or no op. Okay? Whereas here, if you have queue access with multiple threads, then full queue and empty queue they make you just wait and say, hey, there'll be some later point where you succeed. Okay? So that's a difference. That's the difference between real difference between a bounded buffer, what we call a bounded buffer, and a bounded queue, is that the bounded buffer is accessed is a buffer between two different threads, multiple threads. Okay? And half synchronized bounded buffer, we talked about that last time. That would make sense when So intuitively, we used this term last time, it didn't sink in, I guess. But intuitively, what might it mean? So there's a producer and consumer. Half synchronized might mean what? One of them waits and the other doesn't. So there is some real-time constraint that prevents an agent from blocking. There's some constraint, and typically it's real-time. Okay? See? I can't block. So it will be an error if my precondition for execution is not true. Okay? And then it's, okay, so that's, okay, so queue accessed by multiple threads, some of which cannot block. Okay, so it's kind of a hybrid between bounded queue and a synchronized bounded buffer. Okay, so we're coming up the stack. We're going from hardware to the OS to data structures, and now let's get to design patterns. And somehow they're related. So somebody want to define the observer? So how many of you? I know those of you who did 401 with me did observer pattern. KMP also does that's observer pattern, right?
Yeah.
So somebody want to define what an observer pattern is? If you were to teach 401, some of you have been LAs and ETAs, and somebody comes to you, what's the observer pattern? What would you say? Yeah.
So the observer basically has a method called notify that whenever it wants to tell its observers about an event, it calls the method with an object representing the event, and then the observer it calls the observer's notify method, and then the observer takes that event and responds.
Okay, so there are observers and observables in observer pattern. Observers have notify methods in them, and those are called by observables. And how does an observable know about the observers?
Call a register method.
So there's a registry method in the observable. Okay. Now you OS guys you heard the term callback. Can you relate callback to the observer pattern? Yes.
So callback would be like a method that the observer calls once it's done processing whatever is observable.
So you're saying callback is the method that the notify method calls?
Oh, sorry?
So he said that every observer has a notify method in it, right? That is the method required to notify it about some interesting event,
Yeah.
which is passed as an argument. So you're saying the notify method, after the notify method is finished,
It executes the callback.
it executes the callback method. So that's one definition. Okay.
So it's the code that the observable thing registers saying, hey, when this event happens, I want this to happen. I want this code to run to handle that event. And that's the callback.
So the event the method that handles the event is the callback.
Correct. It's saying,
So the
hey, call
notify
this
method-
when this thing happens.
So the notify method that he mentioned is the callback.
Correct.
Correct. That is right. Okay. So the callback is another term for notify method, except callback is also sometimes called an upcall. What would that mean? Upcall meaning what? Up and down, what kind of chain?
Because like some kind of the way I see it is kind of like if you have like a parent process waiting, you might call like exit so you know that the child like successfully completed.
Okay, so you're into the thread coordination and process coordination, and you're saying that you gave me earlier an example where a parent thread waits for the child thread to finish. And now you're saying if the parent thread is interested in the child thread finishing, rather than waiting, it gets a callback. What typically happens in a callback is that the callback executes in the same thread that invoked it. So up and down,
It's like a procedure call, so it's like procedure call you return to the stack, and for opcore is like a late return.
upcall is a late return.
So basically the program call this function just keep going and until get the results for that.
Okay, so what you're saying is that when you're doing some kind of asynchronous invocation, which is what he was talking about also, then the callback is how you get the result back. Okay? I'm saying the callback is a special kind of callback and upcall are the same term and they're both notification methods. So you're saying when the notification happens to be a result of some method you executed, that's a callback? Not quite. I mean, that's one way we could imagine it. Up and down in software engineering, when we talk of up and down, what kind of object are we going up and down? No, semaphore up and down, I hate that up and down. That's like an integer increment.
Layers of abstraction.
Layers of abstraction. Okay? So, an up call would be a so the lower layers are the more fundamental layers, right? Higher layers can see the lower layers. Lower layers are supposed to be oblivious about the higher layers. When you write an operating system, you're a lower layer compared to the application program. So you can accommodate any kind of application program. When you're a kernel writer, you are a lower layer than the OS. Okay? So an up call would be a call from a higher layer to a lower layer to an upper layer. So basically what happens is, this is interesting, right? When you want layer isolation, you say upper layers can call methods in lower layers. Because upper layers know everything about lower layers. They know the API. Lower layers are supposed to be oblivious about higher level layers. Except that they can make up calls. So where's the layering? Well, they don't know what these up calls do. Up call is just saying, call me back. Don't care about what I do. Just call this method. And your functioning doesn't depend on what that method does. When an observer goes and notifies, it just goes and calls all these notification methods. It has no idea what the notification methods are doing. The model is totally independent of the views. It doesn't know how the views will display things. It just knows there are views that need these callbacks. Okay? So that's sort of the callback. So I've gone over, I'm sorry. Object registers themselves with observables. We've seen this. And so we were looking at foundational systems concepts, the ones on which we'll build our distributed systems course on. And I'm just going to do an overview of where we left off here. So we talked about just a queue, okay, and a queue that's bounded. Okay. So that queue, if it gets full, you do give an exception. If it's accessed by only one thread, if it gets full, it'll remain full. If you're trying to add to it and it's full, it'll remain full. So you either do a no operation or you give an error. So that's sort of the classic 410 kind of queue. And then we get into queues that have multiple threads accessing them, and some threads can produce and some threads can consume. Okay. So then what you do is that when the queue gets full, you can say, I'm not going to just give an error, I'll just wait for it to be non-full. Or if you want to consume something from the queue and it's not available, you say, well, I just won't give an error, I'll just wait for it to be non-empty. Okay? So that's your bounded buffer. That's what we call a bounded buffer. And it's synchronized. Okay? And then we talked about half synchronized bounded buffer, where we said, well, maybe some agents can wait and some can't. And so it behaves like both kinds of queues. The ones who can't wait give some kind of error or don't do anything. So queue accessed by multiple threads, some of which cannot block. And full queue during enqueuing and empty queue and dequeuing results in blocking for some threads and errors or no ops for others. Okay? So that's sort of the new kind of queue that we were looking at. Okay? And it was motivated a lot by interrupt processing. That if you're a device and you have raised an interrupt, that has resulted in the execution of an interrupt handler. That interrupt handler is executed by some thread, and the question is, and this thread is either consuming or producing, and the question is that thread allowed to block? Okay, and blocking that thread seems wrong for so many reasons. Okay, here's an interrupt that occurred, and that might be a user level thread, and that user level thread is just that thread that was executing. It was not some selected user level thread. So suddenly that thread that thread is now being delayed, maybe forever. Okay? So that doesn't seem fair. Interrupts, when they execute by disabling other interrupts, so that only one interrupt is executed at one time. So while if you block that thread, then interrupts will be disabled forever till it gets unblocked. Okay, and the condition for unblocking may be the result of servicing some other interrupt. So we get into a deadlock situation where we've blocked this thread, interrupts are disabled, and some other interrupt, if it was serviced, could go and change the condition that would allow this thread to proceed, and it will never happen. Okay? And what's really happening is that, and also you may lose interrupts. So some device has got data, it's trying to interrupt, and that device, could be connected to some agent that can't be controlled. So it can be a human being that's typing away. A human being can't be blocked, threads are blocked. Okay, so if you block this servicing, then you might lose data. Okay, so somehow you have to give feedback to the other agent saying, hey, slow down. Okay, so so that's the half synchronized bounded buffer. Okay, questions? We did this before. I'm just reviewing it. And you guys who've been talking about threads and reading threads and selected threads, you've used the Java array blocking queue, and I've told you guys to use it in a half synchronized fashion. I've told you that the selecting thread shouldn't block, but your reading thread can block. Okay. And you've seen that there are synchronized operations, put and take, and there are non-synchronized operations like add and get. And I want the selector to go and call the operations on the left, the selecting thread, and I want your reading thread to call the operations on the right. Okay? And the reading thread will just do a get, right? Take. So you understand that put and take will block, and add and get will not block. And this is something given to you by magic. You don't have to worry about blocking. But let us worry about blocking. How do you think put and take are actually implemented? How is blocking implemented? We've seen how the kernel implements blocking. It disables interrupts. Okay, when interrupts are disabled, you don't get clock interrupts. When you don't get clock interrupts, you don't reschedule. Okay, because clock interrupts result in rescheduling. So if we are in the kernel or the operating system, we can do blocking, because a thread is just a data structure, it just gets put in a queue. But now array blocking queue is something that some mortal programmer like us wrote. And how did they write? How did they really go and implement the blocking semantics? Or how could they have?
Whenever you call take, they can just check to see if there's like an X element in there that actually available. If it is, we can just read it. Otherwise, we can just wait.
Okay, so that's the question. And try to raise your hand before answering. So if there isn't, we want to wait. How do we wait? Okay.
Just like spin an infinite loop.
You can spin an infinite loop.
Okay. Break out when you.
And so just keep checking and maybe do a sleep in there.
Yeah.
Sounds like a good, robust solution. One person knows why not. Anybody else? Okay, how do you do it, do you think?
From there, we could, instead of like just doing a OAuth and a busy wait, we can dispatch something else to be run. So we can dispatch our producer there, so we don't.
Who's the we here? I'm just. This is the take operation that's being executed in user mode. So it doesn't have access to context blocks.
The thread it made the take send a signal to the
signal. Okay, how do we send the signal? I mean, it wants to wait. So what is the signal exactly? The signal.
Either an interrupt, or in this case, we can just properly change that and say, hey, there's something.
So somehow what you're saying is that let the kernel be an observer of it, and it sends a property change event to the kernel is an observer, and it goes and blocks it on the property change event. So somehow, so what do you think happens in Java exactly? Those of you who did 401 from me, I guess I was not good enough to sync these concepts in your head. You've seen these concepts. And you guys who've done operating systems have seen this concept too. What are the operations available in an object? Any object? There's toString, there's equals. Any other operations available in Java? Whose names may correspond to something you want to use here? Okay, you OS guys. Okay, go ahead.
Wait.
You tried it out. Eclipse told you that.
Yeah.
Isn't this fantastic? You know, my whole principle, you know, in 401, I've gone from giving lectures to telling people, just use Eclipse to learn. Often they will ask me questions about some programming language concept, and I have to reason it out. And the compiler and the Eclipse will just tell you the answer. And that weight will correspond to what you, and those of you who did operating systems, you're getting the observer pattern, but what kind of synchronization mechanisms have you learned in operating systems? What's the first one you guys learned? I mean, the most basic one?
They keep saying busy waiting.
Busy waiting, okay. The bad one? Semaphores? And what else? Some,
Monitors,
does Java have monitors?
but
It does?
Yes, yes.
What is the monitor operation in Java to wait? A signal?
Oh, yeah, it's decommissioned.
It's wait and notify. Okay? So that's exactly what it is. Okay? So how's blocking implemented? Every object has a method called wait, which you guys have just ignored. It's interesting how, you know, whenever we go and invoke an operation on some object, Eclipse will tell you what the alternatives are. And clearly we guys have blinders here. We know what we can ignore. So you guys have just ignored the wait and notify all, but there were three operations that were always available to you. And wait will just say, please block me. So rather than going and sending a notification to the kernel, you know, what kind of notification is that? And the notification going and then blocking you. And you don't want to go and tell a lot of observers. You just want this operation to happen. So it goes and tells the kernel underneath that put me in a queue. I don't want to proceed. Okay? And then what do you think notify does? DQs. Now, notify doesn't take an argument. So notify will DQ whatever, sorry, the first one. So wait will put you in a queue, notify will DQ. And notify all will do what?
DQs them all.
DQs them all. And those of you who did 401 with me, you guys did actually synchronized clapping, I guess, in your assignments. You were one after I was clapping, the other was synchronized with that, and that was all done through wait and notify. Okay. So now let's go and see. Put will do what? Put will go and check whether the buffer is full or not, and if it's full, it will do a wait. Similarly, take will go and check if the buffer is empty or not. If it's empty, it will do it. And who will do the notification? Somebody who's not answered? We need more participation from question answers too. So wait. So put is waiting for non-full. It should unblock when take is executed or when get is executed. Okay. And similarly, take is waiting for non-empty, so it should wait for so the methods that add elements should notify. Okay. So put and take execute waits. They also execute notifies. Okay? And the add and gets will just execute notifies. Okay? So some of the magic behind blocking in Java, you can implement your own blocking semantics. That's nice. Okay? And this is really a monitor. I haven't told you all the subtleties of this. This is sort of my 401 level explanation of synchronization.
I was just going to ask, I know Java has sort of a synchronized type. Does this functionality sort of play into it? No, I'm just curious if it's something that...
Okay, so let's go into synchronized type or synchronized keyword.
Or the keyword rather, not type.
Yeah, so can you guys relate this to the synchronized keyword? So what does synchronized keyword mean in Java? Yeah.
So isn't synchronized implemented by using the objects like intrinsic lock? I don't know if that's the same.
Okay,
as the monitor,
okay.
but only
So
a single thread can access like a synchronized object in the case of.
So is it
a
synchronized object or
expression.
synchronized method we are talking
Well,
about?
there's a synchronized expression and then synchronized method.
So let's
That
just talk
one
about synchronized method right now. Synchronized expression, it just says that take this particular piece of code and put a lock around it. So let's not get into that. I mean, that's just an extension of that. So when I go and make a set of methods synchronized in a class, assume these methods are instance methods. What does that mean? And you're there, so why don't you just complete the story?
Well, the resources being accessed in those synchronized methods can only be accessed by whatever thread is calling that method.
So there's
Or object.
so there's the object with methods A, B, C, D, and E. A and C are synchronized. B and D are not synchronized. What does it mean to execute a synchronized method now? Be a little bit more precise. Yeah.
Only one thread can execute it.
Execute it. I mean, what is the it?
Synchronized method.
Okay.
At a time.
So only one synchronized method of an object can be executed at one time.
Or,
That means only one thread can execute.
yes.
Okay, so there's a lock, like you said, and you get the lock whenever you execute a synchronized method, and any other synchronized method will check the lock. The non-synchronized methods will not check the locks. Okay, why would you ever have some synchronized methods, some non-synchronized methods?
Maybe the non-synchronized methods don't like do anything to the data structures, they just like peek at the
Peak,
front of the
maybe,
queue.
So if I'm giving a lecture and I haven't quite finished the lecture, maybe somebody's listening, and it's no harm done if they listen to partial transaction. With synchronized methods, we're both changing the thing, and which way should it go, this way or this way? Okay, so we understand what synchronized methods are, and that is why Java object in Java is a monitor. What's a monitor? Monitor is a module with some entry procedures, which means some methods execute atomically. Okay?
Object is a monitor in Java. Does that mean like literally every object that we make is a monitor?
Java, so there was small talk. There was, okay, what is the first O language, by the way, you guys? Small talk? That was a trick question. I say small talk, and then I go and say, which is the first object-oriented language? I heard,
I mean, small talk is the language.
he's Googling while you guys are thinking. Google is just, it's a great thing for facts, but what I hate is that firstly, it doesn't allow interesting conversations. We go to lunch and I want to have an opinion, I want to debate, and if you just get the answer, you can't debate. You can't debate on wrong points at least. And sometimes you don't think. Okay? So, but this is actually a factual question. I mean, this is not something you can derive. So what's the first on that?
Similar.
Can you finish it? What's the similar what?
That's
Similar 67. So which year was it done? 67. Okay. So there is object-based programming, there's object-oriented programming. Similar was the first language with classes and objects. Smalltalk was the first one. Smalltalk was the first one with inheritance. Okay. So going back to this question about, in everything, every object is a monitor. So Smalltalk, every value was an object. Even an int was an object. You don't have this int primitive type and an integer type, the class, and have this wrapper types. And you wondered why Gosling did that, because Gosling was the inventor of Java, was being a little pure compared to C++ at least. And I don't know what was going through his head. Firstly, he created this language for himself. So he didn't create a language that we can all debate on later and hold him accountable for. He was just creating set-top boxes, and he wanted some programming language for the set-top boxes. And he didn't like C++, so he invented, and he wanted something to run everywhere, so he invented Java. And then this was around the time that the web was created, and they didn't know how to do graphical user interfaces, so Java ran as applets on the web, and it created graphic user interfaces, and that's why Java took off. And somebody like me who was a Smalltalk fan was waiting for something to replace C++ and was so happy that you could have a more decent language, or language I like better. So, and I believe one of the reasons why he didn't make everything an object was that objects are monitors. I believe that's what it is. Okay? I'm going a little bit on a tangent here. So when Java got invented, we saw that it had monitors, but the classic monitors came from a language called Mesa. Mesa was invented in a company called Xerox, okay, which also invented Smalltalk, which invented so many wonderful concepts. I couldn't make any money out of any of these concepts, unfortunately. So, and it had only one condition queue. You said wait, you didn't say wait on this condition. And Kevin and I looked at this and said, what's going on? I mean, we've all learned that a monitor should have multiple conditions, and why does Gosling have only one condition? So the wait doesn't take an argument, and after some thinking, we couldn't come up with a good problem that required multiple conditions. As it turns out, Gosling was very smart. He just figured he didn't have to have multiple queues. Okay, there's only one wait queue and only one other queue, synchronizing queue. We don't have arbitrary number of queues. Okay, so anyway, I'm going a little bit on a tangent, not quite. So we kind of know now how wait and notify, at least the API. Okay, those of you who've done operating systems, you know, and it's not a mystery to you guys too. What does wait do? It goes and takes you from the ready queue, puts you in a wait queue. That's it. Okay. Okay, now it's synchronized. How does the wait, how does the take and put operation relate to synchronized? As it turns out, these two operations better be executed in synchronized methods. Why? Yeah.
Because if they're synchronized, that means that you're preventing more than one thing from being notified at this. So first of all, if you're running like put, for example, in two different places at the same time, one of them might not block on the fact that, like, say one space, but put's running in two threads. I'd say it would be like this scenario, and then that would mean that they would both try to put whatever object is being placed into the queue, but then the second one would try to place into a now full queue.
Okay, good. So you're saying put should be a synchronized method because we are putting into it, we are changing some data structure. It's a writing method. We don't want two puts to be done at the same time. We don't want two takes to be done at the same time because they are changing some shared data structure. In this case, what we've got is a queue, bounded buffer. We don't want these two methods to be executed, two puts to be executed at the same time, or even a put and a take to be executed at the same time. Okay? As it turns out, even the add and get methods have to be synchronized. And that also makes sense because they change the data structure. Suppose these methods weren't changing the data structure. Let's just assume, I'm changing the problem a little bit. What I'm trying to say is the following, and this is not a great example to show that. Any method that executes wait or notify must be, or put it another way, wait and notify should only be executed in synchronized methods. Even if those methods don't change any shared data structure. As it turns out, our methods all change shared data structures, so it's not a good example. But if wait and notify are not executed in synchronized methods, you will get an illegal monitor state exception. Okay? 1. So wait and notify, when they're executed, they should be, yeah.
We should technically call wait from two places at the same time from different nodes. If it wasn't synchronized, then we would put it at the end of the queue.
Okay, so that's interesting. Which queue? So you're saying, what if two waits are called simultaneously? And then you talked about a queue. What queue are you talking about? The wait queue. There is a shared data structure between notify and wait. The shared queue, which we don't see. Not our array blocking queue. That's a queue of characters or something else. But the wait itself is corresponds to an operating system queue. And we want atomic access to that queue. And that is the reason why we want them to be executed in synchronous methods. Okay? And that's assuming that the queue is kept in user space and not in kernel space. Okay, if the queue is kept in kernel space, and that would make it even objects even more expensive, because the queue is kept in kernel space, so they're actually taking so much space in kernel. That's because it's being kept in user space. Okay, and so we want to guard it using user level routines. If they were being kept in kernel space, then system calls themselves will make sure that their access is atomic. Okay, but since they're being kept in user space, we want that. Okay. Okay. So we synchronized. A single synchronized method can be executed on an instance at any time. You can execute different synchronized methods on different instances. Okay. That's why you need so many queues. Okay. So wait blocks the thread that executes it, usually after checking some conditions. So a method won't just go and say wait. It will say, let me go and check some condition. And it wants to check that condition also in an atomic fashion. Okay, so that's why synchronized methods make sense. Notify, unblock either one or all threads waiting. Okay. So wait and notify all. This grammar is a little wrong here. Share access to a common queue in which waiting processes are put, threads are put, and because they share access to a common queue, they should be executed by synchronized methods of the same instance. Okay, so that they are executed atomically. Okay, and we can have atomic access by disabling interrupts, but that's very coarse grained. That means all threads on the computer stop, in the JVM stop. If you're talking about JVM, actually, sorry, this is at the operating system level. So all threads stop, whereas here we can stop only certain threads in a certain JVM. Okay.
So I have one question. So as a single synchronous method can be executed on multiple instances at the same time?
No, on a particular instance. So different instances have different queues. So I can have, yeah, go ahead.
I'm just wondering if a class have a synchronous method and it has several different instances.
So a class A has got several instances, small a, small b, small c.
Yeah, and can a instance A execute the method A and instance C also execute synchronous method C at the same time?
Yeah, so can two instances execute the same synchronous method at the same time? Now what do you guys think the answer is? Yeah.
Yes, because they have their own queues.
They have their own queues. Okay. Now, if it's a static method, then you can go and say that the queue is kept with the class. But right now, you create. That's the difference between monitors and the Mesa monitors and Smalltalk monitors. In the Mesa, there was no difference between a class and an instance. Everything was a class. Okay. Whereas with this, there's classes and instances, so it doesn't need Okay, so we've seen notify in Java. You can say notify, and you can do wait. And then, it was pointed out that maybe this wait is similar to, say, the observer pattern. Okay, so we also see notify in the observer pattern. So can you guys try to go and distinguish between the way notify in an observer pattern and notify in a thread context, synchronization context? Is there any relationship? Are they the same? Are they different? What's the difference? If they're
This is kind of going back to like OS stuff, but like my understanding with like in the monitor sense, whenever you make a call to notify or wait, you're not guaranteeing anything. Like before you proceed, you have to make another check. So I think this kind of may like fall in the same fact. Like with an observer, you register that property changement, so you know something has actually happened. So you don't necessarily have to do that check again. But a notify doesn't. Once again, notify and wait don't guarantee anything.
okay, so you're looking at really subtle concepts, which I won't get into. That notify is a hint rather than an absolute, okay? Which means it's not giving too many guarantees. That is true, and that happens in Java. Let's back off a little bit. And notify, in Java implements the hint semantics. Mesa did the same thing. And it used to be the absolute semantics. But let's not get into what these two mean. Let's assume there's also something called absolute semantics where it does guarantee and you don't have to check the condition again. So let's assume for now that notify is giving you a guarantee. Okay? So notify is behaving as advertised, that some condition is true, proceed. Okay? What he's talking about is that when you do a wait, before you do the wait, you check if some condition is okay for proceeding. And if it's not okay to proceed, you wait. Right? When you do a notify, you're essentially saying, hey waiters, your okay to proceed condition is true now. That's what it's really saying. And it may not be true in some level. So in that case, the waiter has to go and check the condition a second time after notification saying, hey, did that notify really mean the condition is true? But in some languages, it is guaranteed. Okay, and those languages happen to be more inefficient. Let's forget that and say that, notify the way it's implemented guarantees. So you do have a guarantee in the observer pattern, and you have a guarantee here also, assuming these notify semantics. So what's the fundamental difference between the two of them? You guys have talked a lot, which I want you, and want somebody else. This is a very subtle thing. I don't think anybody's going to get it quickly. Okay, I'll let you be the.
Okay, so in the notify wait paradigm, you're dealing with threads blocking or unblocking based on the call notify wait, whereas the observable, you have a predefined function that you define.
I underestimated you. Absolutely. Okay, so you got it right away. Okay. So this is, in both cases, we are talking, what's the commonality then?
I mean, both of them tell something and some of them have
Both of them are that means there are multiple things acting together. And they're a way of composing code, right? It's a method of coordinating multiple modules. And in one case, you have multiple threads, and in one case, you have a single thread. When an observer notifies, the notification method is stacked on the observer stack. Same thread is used. So we are basically going from intra-thread coordination to inter-thread coordination. Okay? And distributed computing is going to be taking these same concepts and going to inter-process coordination or inter-computer coordination. So when we started off this course, there was this question, is concurrent programming the same as distributed programming? And the answer was yes and no. And, we just see that there's just some subtle differences in implementation and sometimes in design. So we are really going, and people get confused a lot, okay, about these two kinds of notifications, especially in my 401 class where they're so young. and they get to know, see notify method in the same class and notify all observers in the same class, and it gets a little confusing. Okay? So that's the key. Okay? So observer objects, that's the definition which you've seen. And also interrupt routines are similar. Can you guys see how interrupt routines are relate to notify method or the observer pattern? Yes.
So isn't it similar where you're just adding another instruction into the queue of like, hey, I want this to be executed next or as soon as possible?
So that's the trap. You're talking about software interrupt or interrupt? I'm talking about device interrupting. So when a device interrupts, what happens? So you didn't put an instruction in the instruction stream. If you put the trap instruction in your instruction stream as a CPU, yes, the trap handler gets executed. That's like an exception happening, right? But an interrupt, when it occurs, what happens? When a device posts an interrupt, what happens? We spent a lot of time last report. Context switch, and then what executes? The interrupt handler. So the device interrupting is basically saying, hey, I changed. CPU, you are my observer. Go and execute this handler. That's like executing a notification method in an observer. But the device is one thread and the CPU is another thread. Think of them as concurrent activities. So an interrupt handler is like a notification method, except that it's a different computer. It's a device executing. Okay, so you see that there's this relationship that in all cases we are saying there are multiple agents coordinating, whether it's a device and the computer, whether it's an observer and observable, or whether it's a thread and another thread. It's all a question of multiple agents coordinating, and there is some asynchrony there where you don't know when something may happen, and whenever something happens you say, okay, call me back. Okay? So enabling interrupt posts and waiting, saying basically I'm registering myself as and having an interest in some action. Okay? And whether it's in multiple devices or whether it is in the same computer, and when you go and execute handlers or you unblock or wait, it's like executing a notification method. Okay, so there's this commonality in all of these things. And when we go and study remote procedure calls, that's just going to be a method executed in another address space. Okay, very similar to interrupt handling. So when you have trap handlers, that means within the CPU you're going to saying trap. You suddenly start executing some other piece of code. You had an instruction stream, suddenly you go to a trap handler. Okay, that's within the same thread. So that's and interrupt handlers and wait notify do inter-thread thing. And also a little difference, when an interrupt occurs or when a trap occurs, you execute only one piece of code. Whereas with notify all, you could go and have multiple reactions to the notify all, and with observer pattern, you could have multiple reactions. Yes, that's a relatively minor thing, but there's all this commonality.
So which one is the interrupt one, the observer or the notify?
What do you think? When the observable goes and it executes a notify method. Is it executed in a separate thread or the same thread? Okay, you can see it stacked up. Whereas when you do a notify, some other thread gets out. When you post an interrupt, you're a device. Some other piece of hardware went and executed code. So that is coordination among more loosely coupled agents. But all, the point is that it's multi-agent coordination. Okay? And it's not that, it's the same problem, that these all do different problems. You can do a problem first with all in one thread, and then go and say, hey, I'll have different threads for this problem, just because modularity is better, or I can get better performance. And then you can say, I want to do these tasks on different computers, or one on a device and one on a computer. Okay, so there's just this different levels of coupling. Okay? Questions? Okay. Now, when I talked about the observer pattern, a lot of you said MVC. And MVC is something that you have to use in your assignment. So let's just get a little clear about MVC. Someone want to describe what MVC is? What's a model? What's a view? What's a controller? Yes.
The model holds the state of your application, your data structure. The controller kind of handles communication between the view and the model, and then the view is like active.
Okay. The model is what holds the semantic state, should we say? Every object has got some data structure. So we can go and say that there is some semantic state that is displayed to the user. So the model holds the semantic state, and the view does what? Renders it. We agreed there. Now we'll get into a little war. You didn't do 401 with me. You did with KMP. Okay? And your answer reflects that. Okay, guys. He remembers it though. So KMP was very effective. Anybody remember what I said about what a controller does? You guys have gone and done web programming after my course. So what's the inverse of output? Who handles input in this MVC structure? View. View by its name means UI, means display, rendering. So why is the view doing the input?
You just capture the input, the controller is the one that actually processes it.
I don't know. He said the controller is the one that coordinates the views and the models. So there's two viewpoints on MVC, and KMP being much younger than me uses the latest and I won't say best viewpoint. So I've gone and put the word small talk here. Okay, being a fan of small talk, and the word MVC was invented in the context of small talk. Okay, if you look at any research paper, that's the classic papers there. And it was based on the idea of views and controllers. It didn't look at all the problems the web creates for you to implement the proper architecture. And in this architecture, the controller is the one that does the input. Okay, you can imagine the same object and the same UI having multiple controllers. You can imagine having keyboard shortcuts. You might imagine having menus. You can imagine having buttons. There's no reason why one object should go and present all of these things. So you want to be able to have modularity where you can have, you don't have a binding between views and controllers. Okay? So view is something that displays output. This architecture is very easy to explain. It's very easy to argue for, and in fact, you guys know that which is the company that's made the most money out of all the ideas of small talk, and often claim credit for them. The richest company today. Okay. So Steve Jobs went to Xerox and said, "Aha, this is something that can make money. We need it." Okay. And for a while he didn't, though, but ultimately the company did. So if I think Apple's version. So you see the MVC is something that the mobile computers use a lot and also used in the web, and Apple's versions, I believe, are Smalltalk inspired completely. So when they talk about MVC, this is the MVC they're talking. Okay, so when you have an input, the controller intercepts the input and it doesn't know anything about any view. It just invokes a method in the model. The model goes and informs all the views, which know nothing about the controllers. It's a beautiful discovery. Okay. However, field evolves or devolves, I don't know which way you want to look at it, and now we have the controllers accessing all the views. And the reason for this is the following: that when you build a web application, you want to build a model, a server, and you want to build views in the browsers, and you want to have multiple uh, you want to have maybe multiple views in the browser. The trouble is that the server cannot invoke a callback or a notify method in the browser. That's just an artifact of the web architecture. So the controller in your browser is the one that knows about all the views in it, and after it modifies, changes the model in the server, it goes and updates, goes and tells all the views. That's my best guess as to why they let them change this. I wish they had used a different term for all this stuff, but they went and stole Xerox. People stole them from Xerox in so many different ways. So they stole the MVC term from them too, and just confused the hell out of me, you know. And so KMP and I got talking about it, and he was just using controller in this very strange fashion. So then we went and looked up and reconciled things. This is how things have evolved. Okay, so when I talk MVC, this is going to be very orthogonal to the course, but the implementation you have has got MVC in it, and the controllers and reviews are following the Smalltalk MVC. Okay, and when you guys go and program on mobile computers, just be aware which MVC it is. I won't be surprised if all of the mobile computers use Smalltalk MVC, and the web guys just have their own MVC structure, which is different. Anybody programmed on Android? So what do they mean by a controller there? Sorry? So they do it right. Okay. So okay. And I assume the one you talked about is used in the web. Your definition, I assume.
Yeah, I mean I had Cambridge before, so.
But you also had him for the web course afterwards, right? Yeah. So he uses them consistently there. Yeah. So just to make things very clear about the MVC and observer pattern, and you'll see this in your traces, that here we have, before any input occurs, there's a meaning of life model example, and we can look at the traces now and understand them a little better. And we have, so I forgot to do this, but I should talk about how these traces are structured. So every trace action starts with an I triple star, that means information. You can also get E and warning and error. And then within curly braces is what, for those of you who've actually looked at the traces? So there's a method name within curly braces. There's a method name. There's something else after that within parentheses, and then there is event source parentheses and something else. So within curly braces is not method name, it's something else. Thread. It so happens that this is it's all being done under the main thread. So that's the main thread. Added property change listener is actually anybody want? I explained that in the document. Anybody remember? No. So in a trace, I'm describing some event. So within curly braces is the thread that announced the event. Okay, and within the first pair of round parentheses is what you would call event name. Okay, that's the event name. And then event source would mean the class. Okay, so main is the thread, that is the class, and then arguments. Okay, whatever they are. Okay, so this is going to be very useful to you guys. Trust me. Okay, because you can't put debugger, you can't often put breakpoints. And so this tells you that, hey, look, the main thread added a property change listener, and this method was called in the meaning of life model. Okay, the model is the one that registers listeners. Okay, model is also an observable. It's an observable and it's a model. Okay, and we've added two property change listeners. One is the view, and one is our sender object. Okay, and you guys have to do the same thing. And the way our grader will try to ensure that you guys are following the right path is to look at your traces and see whether things happen in the right way. Okay. And then 42 is the number that's input by the user. So the controller accesses it. The controller makes no announcement, but the controller goes and calls a setter method, appropriate setter method. The setter method that's called here is by the main thread. It's called set property. Sorry, the event is set property. The class is a meaning of life model. We don't know which method in that class got called from this, and it has an argument which is the meaning equals 42. Okay, so the meaning is the property name and the value is 42. Okay, and whenever the set method is called, it goes and notifies its views, and that's what's happening. Notify property change event called by the model, and its arguments are the property change event and the array of all listeners. So this is a very long piece of long trace here, because it's telling you not only what the event was that is announcing, but who the event is going to. So this is a way to go and, initially I got some questions saying, hey, I can't make any progress, this is blocking here. I said, just give me the trace. And when the person saw the trace, they said, oh, I guess I know what the problem is. Okay? So the traces are very useful here. So please, in your assignment submission, you have to make, I didn't enable tracing by default, so you have to enable tracing. Okay, it needs to be graded. So the view, one of the view gets the output and it goes and prints out meaning of life 42. Okay, so one object processed 42, another object decided what to do with it, and the third object that you displayed. That's your MVC. Okay. Questions? Okay, we saw this last time. Let me go and recap it. The term callback has been used for a long time, which is basically, again, it's related to the observer-observable pattern, and callback is just a method invoked in a higher layer. Okay, so if we layer things, the lower layers are the ones that are system layers. They don't depend on the application layers. The higher layers are sort of the client layers, if you will. They depend on the lower layers. So normally when dependencies are captured by method invocations, so you say, okay, the upper layers can call methods in the lower layers because they can see them and they can call methods in them. Lower layers are not supposed to call methods, but they can call callbacks. Because callbacks, the lower layers are not dependent on what the callbacks do. Okay, they're just saying, here's some information for you, and I'm just supplying the information through a notification method. I'm not depending on anything that the notification method does. The notification method can do anything it wants to. Okay, so there's no dependency. So we still have a layered architecture even though the calls are going in both directions. Okay, so the callbacks are also called upcalls. Okay, questions? Okay, so if I was to model a callback, I would model that as a method in an object. I can go and make, now especially with the new version of Java, I can make, I can go and pass methods as parameters. But before you could do that, I can imagine just defining that as a method in an object. Okay, that's what your view object is, right? It's an implementation of the notify method. The notify method is the one that takes parameters, and the caller of the callback supplies the parameters, saying, here's something about me that you're interested in, so I'll pass that information in your callback. Right? Everybody fine with that? Now, I've gone and put the word command object. And again, those of you who have forgotten my 401 should know a little bit about what a command object is, and those of you who've been doing assignment 1 might understand what a command object. Anybody Google for command object and try to understand what it means? Okay. So, what's your intuition as to the difference between, I'm going to call this thing as an action object, one that captures an action, okay, notify action. What do you think a command object is? One person's totally aware of what's going on. Anybody else? Okay.
So I love the way generally or the way you structure it?
Why don't you describe both?
So the creation of a particular command object, you initialize methods. Initialize or initiate by When you, I think it was when you queued it, either queued it or registered it, then you would call that initialize method and you would perform some set of tasks of some sort related to that particular command option. And then when that task was later dequeued from, or by the selecting thread, then it would call the execute method. So that's similar to your case.
That's how I used it. I had some execute method in it. And how do you, and generally what would be a command object?
I'm sorry.
You said, do you want to know how I did it, or do
No,
I
that
want?
was how you implemented it.
Okay.
I didn't know that you.
Okay, good.
Concept.
So now that you understand what he said, that command objects got queued, and when they got dequeued, an execute method was called on them. At least you now understand what did that mean. Given what he said, this command object does, can you tell me the difference between an action object and a callback object and a command object? The execute method that was called, did it take any parameters? No. So that's the key. The execute method doesn't take parameters. So now can you try to, as generally as possible, tell me the difference between a command object and an action object? Think of,
The command object probably contains the details you need to execute internally, while the action object might depend on some dynamic parameters that you use.
okay, so the execute method is more parameterized than the. Think of English language. Think of verb. Think of a transitive verb. Transitive verb. You guys know what a transitive verb is? You guys, the way I studied English was formally, so we were given all these definitions, and then we learned how to use it. Whereas, at least in my initial classes, so transitive, yeah.
A transitive verb is when it requires an object. So it needs to act.
So the transitive verb is the one that has an object. Okay? Put the glass, not container. So now if I was to say that a callback object is a transitive verb, then a command object would be a no. Oh, would be intransitive? That's one way to look at it. Yes, that is indeed one way to look at it. Or it could be not a verb. It's a command. A command is a sentence. It's a verb with the object. Okay? So think of an action as being a method, and think of a command as being a method call. A method call specifies both the action and the parameters. Method just goes and tells you the name of the method. Okay? So if I go and say put, that's an action. Okay? I have to go and provide the object later. In both cases, we're talking about transitive. And put A is a command. And I want an object to go and capture the command itself. Not the parameterized thing, but the one that's been supplied the argument. Okay? So command object is a method plus parameters. It's a method call. Okay? Now it can take a constructor that goes and says what the parameters should be of the actual action that it's doing. Okay? So there is some method that's going to execute, and it's got an execute method that takes no parameters. That execute method, like any method in a class, can refer to instance variables. Those instance variables can be set by constructor parameters. Okay? And that's what a command object is. Okay? Constructor can take target object and parameters of operation as arguments. Whereas a callback is an operation that can be invoked on many different arguments. They can be invoked with many different arguments decided by the calling service. Okay? An execute method, you just have no choice. The caller has no choice. Okay? Command is an operation whose parameters are decided by the command or its creator and not the calling service. Okay, so there's some service that is invoking it. The service doesn't decide what the parameters are, it just calls the execute method. And the object on which it's calling decides what the parameters are. We run out of time. but you've all used command object. Okay? Or at least that was a prerequisite. And we'll see how next. Okay. So if I was to model a callback, I would model that as a method in an object. I can go and make, now especially with the new version of Java, I can make, I can go and pass methods as parameters. But before you could do that, I can imagine just defining that as a method in an object. Okay? That's what your view object is, right? It's an implementation of the notify method. The notify method is the one that takes parameters, and the caller of the callback supplies the parameters, saying, here's something about me that you're interested in, so I'll pass that information in your callback. Right? Everybody fine with that? Now, I've gone and put the word command object. And again, those of you who have forgotten my 401 should know a little bit about what a command object is, and those of you who've been doing assignment 1 might understand what a command object. Anybody Google for command object and try to understand what it means? Okay. So, what's your intuition as to the difference between, I'm going to call this thing as an action object, one that captures an action, okay, notify action. What do you think a command object is? One person's totally aware of what's going on. Anybody else? Okay.
So I love the way generally or the way you structure it?
Why don't you describe both?
So the creation of a particular command object, you have your initialize methods. Initialize or initiate. When you, I think it was when you queued it, either queued it or registered it, then you would call that initialize method and you would perform some set of tasks of some sort related to that particular command option. And then when that task was later dequeued by the selecting thread, then it would call the execute method. So that's similar to your case.
That's how I used it. I had some execute method in it. And how do you, and generally what would be a command object?
Sorry.
You said, do you want to know how I did it, or do I want?
That was how you implemented it.
Okay.
I didn't know that you.
Okay, good. So now that you understand what he said, that command objects got queued, and when they got dequeued, an execute method was called. At least you now understand what that means. Given what he said, this command object does, can you tell me the difference between an action object and a callback object and a command object? The execute method that was called, did it take any parameters? No. So that's the key. The execute method doesn't take parameters. So now can you try to, as generally as possible, tell the difference between a command object and an action object? Think of
The command object probably contains the details you need to execute internally, while the action object might depend on some dynamic parameters that you use.
okay, so the execute method is more parameterized than the. Think of English language. Think of verb. Think of a transitive verb. Transitive verb. You guys know what a transitive verb is? You guys, the way I studied English was formally, so we given all these definitions, and then we learned how to use it. Whereas, at least in my initial classes, so transitive, yeah.
A transitive verb is when it requires an object.
Okay.
So it needs to act.
So the transitive verb is the one that has an object. Okay. Put the glass, a container. So now, if I was to say that a callback object is a transitive verb, then a command object would be a no. Oh, would be intransitive? That's one way to look at it. Yes, that is indeed one way to look at it. Or it could be not a verb. It's a command. A command is a sentence. It's a verb with the object. Okay? So think of an action as being a method. and think of a command as being a method call. A method call specifies both the action and the parameters. Method just goes and tells you the name of the method. Okay? So if I go and say put, that's an action. Okay? I have to go and provide the object later. In both cases, we're talking of transitive. And put A is a command. And I want an object to go and capture the command itself. Not the parameterized thing, but the one that's been supplied the argument. Okay? So command object is a method plus parameters. It's a method call. Okay? Now it can take a constructor that goes and says what the parameters should be of the actual action that it's doing. Okay? So there is some method that's going to execute, and it's got an execute method that takes no parameters. That execute method, like any method in a class, can refer to instance variables. Those instance variables can be set by constructor parameters. Okay? And that's what a command object is. Okay? Constructor can take target object and parameters of operation as arguments. Whereas a callback is an operation that can be invoked on many different arguments. They can be invoked with many different arguments decided by the calling service. Okay? An execute method, you just have no choice. The caller has no choice. Okay? Command is an operation whose parameters are decided by the command or its creator and not the calling service. Okay, so there's some service that is invoking it. The service doesn't decide what the parameters are, it just calls the execute method. And the object on which it's calling decides what the parameters are. You run out of time, but you've all used command object. Okay? Or at least that was a prerequisite. And we'll see how next time. So I introduced last time the notion of a command object, and you know, those of you who've started your assignment, that there are command objects involved. So let's try to understand them. And I started out from the idea of a notification method and an observer. And a notification method is something that some lower level layer, perhaps if it's a callback especially, but some layer calls on another, some object calls another object. So object A calls on object B without A being at all aware of what B is about. Okay, it makes A independent of B. It just says, hey, B, I've done something. Here's some information that is relevant to what I've done. And in case you're interested and want to do something in reaction, as a reaction to that, go ahead. Okay, I don't in any way depend on that. Just return, okay, because it'll be executed as part of my thread. So don't just hang forever. And I'm just calling that an observer or a callback object that has this method, and I'll call it execute, no name. Okay, who knows what it's supposed to do? We can call it notify, and it takes some parameters as arguments, saying this is the information of interest to you. Okay, this is how the action is described. And if you know the observer pattern, that's easy to figure out. And then I said that's and so that's almost like a command object, but not quite. So if we think of this kind of object as providing a verb that somebody else has to fill up. Okay, so the callback object provides a verb, and the object is provided of the verb is provided by the caller. A command object is the whole sentence, if you will. It's the whole command. It takes no argument. Okay, so it also has a no name execute method, which means who knows what it does, and we don't even supply it any parameters. Okay, even if the underlying operation has to have parameters, we don't supply it. If there are parameters that this object is customized, those parameters are provided through the constructor, and maybe even the object on which you invoke the underlying operation is provided at construction time. Okay? So constructor can take a target object and parameters of operation as arguments. Okay? So we can think of every operation being executed on some target object and having some arguments. So all of that is hidden in the execute method. Okay, whereas a callback is an operation that can be invoked on many different arguments decided by the calling service. So the calling service decides what the arguments are in the case of the callback object, but the calling service doesn't supply the arguments. Okay. So my last question to you was: have you guys seen command objects before this assignment? And I claimed you all have, especially anybody who's written any part of the assignment, has written some of the important parts. So somebody want to fill in the gap here and say where you might have used a command object? So you obviously used, the command objects underneath the NIO manager layer if you started implementing the assignment. But I'm saying even before that, before this course, you probably used it. So what is the one thing I required you guys to know before coming to the course? Which I haven't spent any time discussing so far. Not really. Sockets, you guys with networking knew. So we'll derive sockets from first principles. Threads. Okay. So can you relate threads to command objects? Or if you can't, how did we define a thread? So we defined a thread in an intuitive way. So how would you define a thread, and how do you guys construct threads in Java? So the two related questions. So what's a thread defined abstractly? Yeah.
It's a single line of processing with a shared address space. As in, you can have multiple threads that work within a single process.
Okay, so you can have multiple threads within a single process, and each has a shared address space. So that's what is shared. So what distinguishes threads from each other? Yeah. They have their own stack. How is that stack created? So by some sort of manager. But when you create the stack, what kind of, as a user, what do you have to provide to the kernel, to the manager, to start off the stack? Sorry? Okay, so it would be good to have for the thread to have a name. But when you do the main thread, the main method is called with main args. So when you create a thread from a user level thread, the creator has to specify what to the underlying system.
The run method?
Sorry?
The run method? Specific to Java, you provide a
yeah, but just say abstractly. Who knows what a run? Yeah, provide abstractly. What do you have to do? We are talking of creating a new stack. What's the bottom of the stack? But that's the implementation control block. But what is stack? So when we talk about the call stack, what are we stacking in the stack? What are each element of the stack? What is it? What is it actually? Yeah. A method invocation. So you have to go and start off and tell the thread creator what is my starting method invocation. And then that method will call other methods, and we don't have to worry about that. The compiler will take over. And the compiler will go and have code at runtime that pushes elements and pops elements when you call methods and return methods. But when you create a thread is really an asynchronous invocation of a method call. Okay? As opposed to a synchronous invocation. Synchronous invocation means you wait for the return value to come. So you just go and call the procedure, and there's underlying code in the compiler has generated that goes and pushes things on the stack, pops things on the stack. But the compiler always assumes there's something on the stack. The stack has been created. So that's where you as an OS person have to really, create the initial element of the stack, and you have to know what the method and its arguments are. So now can you relate this to command objects? What's a command object?
Is it the stack?
It's a, yeah.
Would the thread dispatcher be a command object?
Thread dispatcher is, so what's a thread manager? You use the word thread dispatcher, thread creator. Somebody is being passed that method call. I don't know what you want to call that. Okay, that's the thread manager. Somebody is passing that method call. Okay, so somehow you have to, give to the thread object in Java a method call. And you see a method call in this picture? What is the method called? Sorry? No, in this picture.
It's the command it's the method that's within the command object here. Because you just have, we're given the full method and all the parameters, so it's already there.
So it's a command object. That's what a command object is, a method call that you just execute. Okay? And it happens to have an interface that Java calls runnable. They happen to call that execute method that I've said was a no-name method run. Okay? But essentially what you're doing when you're creating a thread is doing an asynchronous method call. And what is a command object? It's an object that captures a method call. It's got its own method that you can call to call the method it's capturing, but it's really an object there's something in Java called the method object. Anybody done reflection of any kind? So if you've actually looked at my input processing module that goes in, I've used reflection to go and make it quite general. Okay, have a look at it. It's pretty cool, I think, and the way you did it. So so that's a method object that to which you can pass object and parameters while executing, and you can execute that method object on anything through reflection. So that's what it is. Basically, you have to think about a thread as an asynchronous method invocation, and that's done by some generic system. And that generic system doesn't know anything about what that method is supposed to do. Okay, so it just goes and says, "Give me an object that I can execute," and I don't know anything about what to execute, what to do, but I know how to do something. Okay, and you tell me through an object what that something is, and that something happens to be called runnable. Okay, so let's go and see this properly. We all know that threads are started. Okay, threads that are started are created. We go and pass to the constructor some kind of argument. That argument now we know is what Java calls runnable, what is and more abstractly a command object. Okay, and this tells you that you can, for instance, have a put command whose constructor is passed an argument specifying what is to be put. Okay, and we can have in Java, by the way, this is not real Java. I mean, this is looking like Java. I use Java syntax, but this is not compiled, executed, or anything. This is pseudocode as far as I'm concerned. And so you go and have a constructor that goes and stores its argument in an instance variable. It's going to store it in a global variable because later an execute method is going to be called run. That run method is not going to be passed any parameters because the thread system doesn't know anything about the parameters. But we have stored the parameters of this operation put in our instance variables. These instance variables, global variables, can be accessed by this run method to do whatever the run method what it's supposed to do. And in this case, it gets some kind of buffer in which it puts this. Okay, what that buffer is doesn't matter here. The point is that we are going to actually not make the thread creator, thread manager know anything about the operation. Yeah.
So that example, the put command, is just a way we send the fact method, like what method we want to execute once it starts.
So we are just specifying the what. In general, when you have, there's always a what and the how.
Right.
And at this level, we are just letting the programmer understand the what.
So could you remove like the whole put command thing if we just like functionally, or would this differ from that? Like using a lambda expression?
Yeah, you can use lambda expressions. Okay, so I hate lambda expressions personally, even though I grew up on functional programming more than you guys did. I saw that stuff before OO programming. Right? Okay, and I enjoyed it very much at that point. But they're unnamed. I just like named things. I like them. I don't like inner classes because I'm just all for sharing. If you want to share something, you name it and you go and put it in some public class. Okay. So, but yes, if you know what lambda expression is, that's exactly it. And Java did not have. So C, for those of you who've done operating systems, you know you can just pass the address of a method, of a procedure. And then the question becomes, you know, the user of that method, I mean, what kind of arguments do they provide to it? So that it's not very type safe. And with lambda expressions, you overcome that problem. Okay, that you can actually go and specify something with the body. Actually, you can just pass something that's executed in a much more type safe manner. So this was all before that stuff. So this was Java's way of capturing. And we'll see that we can have more than an execute method in this. Okay, so this is more flexible in many ways. Okay, if you guys, have you guys done the visitor pattern at all in data structures or compilers maybe? In compilers, you do the visitor pattern. Just something similar. Okay, you just visit, just like execute, but you do it recursively. Okay. And also, by the way, once you've started the thread, if you want to wait for the thread, has anybody ever done that? Wait for the child thread to finish? You've done that? Okay. Have you seen the operation? So you can say thread.join. Okay, so you do an asynchronous invocation and then you wait for it to finish and you can say join. Okay. So what we've done is we've made sure that this method that we are calling is executed in a thread that's other than the thread in which than the parent thread. Okay, so I'm deciding what operations to be executed, asynchronous executed, and I being a thread, and thread A doesn't go and execute the operation in its own stack; it executes it in a different stack. And it so happens that stack is a new stack. Okay, so to execute the operation asynchronously, I'm creating a new thread. And this goes back to sort of the issue you mentioned earlier, that should I create a new thread for each received command in our application? So now that we know how to create threads, should we use them with abandon? Okay, and this is very interesting, you know, because GoTo got invented, and then people started using it with abandon, and then people said, no, don't use GoTo as much, or don't use it at all. And then inheritance, you know, I told you similar 67 was created with object to support objects, and then Smalltalk provided inheritance, and everybody started using inheritance even when it didn't make sense. And now, you know, anytime somebody uses inheritance, it's looked at very suspiciously. And so, you know, now that you know all these how to create threads, you might want to create threads with abandon, but threads have a cost, and sometimes you do want to execute operations serially. So in your project, you do want the commands to be executed in serial fashion. Okay, and we are trying to, with the atomic broadcast, we're trying to do it globally serially. Okay, but at least when we are in our own process, we should execute them serially because there's a dependence. If I move something and then I take, that's different from taking first and then moving. Okay, so operations may not commute, and the user has submitted them in an order, so we do want to execute them in that order. Okay, so in this case, what I've done is I'm executing it asynchronously in a separate thread. Okay. Now, you guys who've started on assignment 1 have seen that you can create your own bounded buffer and your own process thread to do them in a separate thread, but not in a new thread. Okay. The selector thread goes and says, okay, this operation I won't execute myself, so here it queues it up for some other thread to take it. Have you guys seen a generic service like that? You've written a special service for yourself. Have you guys seen this done in a generic? Have you seen a generic service to do that, to execute operation asynchronously, but not in a new thread in Java? Or maybe maybe this term you use. I want to see whether you've seen it or you can relate to it. maybe I want to execute a bunch of operations not on a single thread, but on a set of threads. I don't care which set of threads, just not my thread. And I don't want to create a new thread each time. What will the set of threads be called? Workers, good. There's a technical term, thread something. Where did you hear this term?
I think I came across this somewhere, like sometime I was doing something.
Okay. That's very specific. That's called project-based learning, informal learning. A lot of good learning happens that way. Okay. So thread pool. And have you seen it? Have you guys ever, do you know that thread pool service exists in Java? Do you know? Sorry? So I used to implement my own thread pools. There's a lot of things I used to do on my own that Java finally started doing. And thread pool, I've noticed recently, exists in Java. So what you do, have you guys seen this type future? Have you heard the term future in any class, like in programming languages also? So what you're saying is that I've constructed an operation which I don't want to do immediately in my thread. I want to do it, or I don't want to do it immediately. Let's not say in my thread or another thread. I just want to do it, don't want to do it right now. Or even if I want to do it right now, I want to do it later too. So I want to store this object for the future. Okay? So you can go and there's something called the executor service in Java. Okay? So if you just Google for future, you'll go and see executor service also. Okay? And you can just say submit rather than saying new thread and here's a runnable. You go and say, hey, service, submit this particular command object to you. Okay? And then you can later wait for it, just as you could say thread.join. Here you're not joining, waiting for the thread to finish. You're waiting for this particular command object's execute method to be called and for you to be notified. And imagine how this will be implemented. That service will go and do a notify and you will do a wait here. Okay? And everything else is the same. Same runnable can be used. Okay, so this is very powerful. Please, if you guys are using threads, I don't need too many threads, and you're too lazy to create your own bounded buffer, which you should be if you don't need to. Okay, use an executor service. So, for instance, in 401 and even in your class, I hope to have the automatic grader working. So there is some part of my code that's invoking your code. Actually, it won't work in your case because I want to have to invoke different processes. But in the case of 401, I just don't want to use my own thread to execute your operation because you may never terminate, for instance. Okay, and I have to know whether you'll terminate. So I just use an executor service like this and say, please execute it in a separate thread, and I'll wait for so long. And if it doesn't return by that time, I'll say infinite loop. Okay, so same put command will work for the service. So I strongly encourage you to use the service whenever you can. Okay. Now, what if I want to go and wait? Not only wait for the operation to finish, but also want to get a return value. How do you think I would change the API? It's a simple question, not a trick question. What's preventing me from getting a return value here? Execute what?
The runnable action being run. It has to be run for you.
Yes, sure. So we are running it. We are waiting for it to finish. I just don't have a return value. So what do I need to get a return value in this API? So what's the underlying service doing? Is executing run. Yeah.
If you had like just a property in the run could set the property.
The run could set a property, but the run is being called. Can't the run just return a value?
Yeah.
Okay. So I say it's a simple question. It's not a. I know levels of indirection are great. Okay, but in this case we don't need any indirection. Okay, so it just so happens that when runnable was created, they didn't think of a future. Otherwise, they could have had an object returned by run. Okay, and so if you want to do that, retrieve after create. Well, we'll again do the same thing, but we'll get a result back. But now my get command is not runnable; it's callable. I mean, runnable, callable. What's the difference, right? But it's just that a callable has a return value. Okay, and the callable I assume is a generic. I believe it's a generic, so we'll go and just pass it the right type. Okay. So there's runnable and there's callable and they're really command objects. Okay. Now, those of you who done 401 with me, and I've forgotten as I've realized, have actually used command objects something else too. And those of you who done compilers, or how many of you know there's a Java interpreter, there's a Java compiler, and they seem to do different things. But sometimes compilers and interpreters do different things. So anybody want to define the difference between a compiler and an interpreter? Yes.
Compiler tends to take some human readable normally and down translate them. So in the case of Java, the Java compiler translates it down to bytecode, and that bytecode is what's run by the Java interpreter, which is what live interprets and like.
So live, there's a notion of liveness.
Yeah.
So in the compiler, you take some description of what you want done, you compile it, and then you run it. And if there was no Java, forget this two-stage thing. If it's compilation versus interpretation, or the same thing,
Yeah.
an interpreter would do what?
It would take your normal written description. It would run that directly.
Directly. There's no other process will run. The same process will do it. Right? So imagine I'm giving this lecture, an interpreter would take every sentence I've said, and translate it, whereas the compiler will wait for the whole lecture, translate it, and then give you a book and say, okay, read it later. Right? So you tend to do often parsing or line by line. Okay, so your command interpreter, your shell is a command interpreter. Okay, and you can imagine an expression evaluator. You want some complex expression evaluated. You can write that down in a main method, compile it, and run it, or you can just type the expression in a command line and it gets evaluated. Can you guys see, and this is subtle, how a command object could be relevant here? Did you guys ever, in any course you did, look at expression evaluation and interpretation of it? So, today's the day that it wants me to be active. So in functional languages, this happens a lot, by the way. So functional language and interpreters go together. And you guys in 401, you use command objects. Do you remember now at least that command objects were used in the context of threads? Do you remember command objects being used in something else also? See, this is where you need to be quizzed every day, right? And really remember it. So this is how it happens. In functional languages, you say, okay, parser, give me an object, give me a syntax tree. That syntax tree, give me a root of the syntax tree. That syntax tree is not then gone and compiled by some code that goes and generates code. You go and just call a method on that syntax tree saying eval, expression eval, which will go and evaluate a sub-expression, and that's one of the most, in OO programming, that's often used as a classic example of OO programming. And what is eval doing? For instance, I told you this is not real code. So my constructor and my class name are not matching, okay, because I changed the example. But basically, I've got a plus expression, which has a constructor that takes a left operand and the right operand. It stores it in instance variables. The parser constructs this object based on what was given. It doesn't, and it knows this class exists, so it just instantiates this class. And later, when it has to be evaluated, you just go and say evaluate or call. And what does call do? As you see, just says left operand plus right operand. It's doing it right away. There's no bytecode generated, no machine code generated. And does this now make sense? Did you guys ever see a tree function like this? No? Now, notice that this callables is taking as a parameter a callable itself. So the callable is operating on callables. The left operand and right operand are also callables. So you can think of a tree in which the parent node implements some interface, And the children nodes implement the same interface as the parent node. Often when you talk of polymorphism, you talk of this kind of example. And this kind of pattern, again, not familiar, not been highlighted in any course. So I would think that maybe in the compiler course, I have at one time done in 401. That's called a composite pattern. Okay, this is a very important pattern where and actually this is used in the NIO manager. So you've been tracing the code in the NIO manager. Have you traced the code for the write?
Maybe, like what specifically?
I don't know. So if you haven't, so the write command is executed on a buffer, not on the individual ones. The buffer goes and does all the writes to his children. It's the same idea, that the buffer is itself a command object that's calling methods in its subchild objects. Okay, so this is again, this is extremely important pattern, and the visitor that you did, that's an example of a composite pattern, because often the visit in the compiler will go and do visit of the children. So the visit of the compiler will go and do the visit of the children to generate compiled code. Okay, so that's like a procedure. Here we are doing evaluate on the parent to return results, because this is typically a callable, it's a return value thing. The same idea of a recursive composite pattern, not generating code but actually returning a value. Okay. Now, did what? Did you call it the composite pattern? No.
We never mentioned any pattern other than visitor.
Yeah. So visitor is in my mind a subclass of the composite pattern. Yeah.
So evaluating like left operand plus right operand, or left operand and right operand like.
Oh, sorry, I got it wrong.
Is it dot all?
Left operand dot call and plus right operand.
Oh,
sorry,
okay.
sorry. Yeah. Thank you. And if I don't change it, I hope I'll remember to change it. Okay, absolutely. So I hacked this. It was first a plus put command, and I said, put command is too obscure. Let me put something more classic in it, and I made some changes and didn't make all the changes. But excellent. Yeah. Okay. So that's where the recursion comes in. So and this is also neat. I mean, this is so many nice concepts going on. So I love compilers, because this has got the composite pattern, it's got recursion, and it's using polymorphism. And my generation learned OO programming late. Okay, so because OO programming was not in fashion. So we knew all these concepts before we went to OO programming. So the examples used were the ones that we had learned in compilers and other things. Whereas, your generation learned it before you learned compilers, so you use different examples. Okay, but these are the kind of examples we grew up on. Okay, as it turns out, command object will not be used by compiler people, will not be used by thread people, will not be used by future people. Command object is something that I encountered while doing research on distributed undo. So this is actually something related to undo. And the undo people will use command objects and nobody else does. Okay, it's just that I was teaching 401, I was teaching them undo because I loved undo. And then I said, let me teach them threads also. So I said, hey, I can actually economize on concepts by just saying it's the same concept. So you'll never say anybody saying that threads do command objects, except me perhaps, but they do. Okay. So can you guys see how this may be relevant to undo? This idea of a future. Undo, redo, think redo also. So what's the future? Yeah.
Could you just pass a command that has a command inside it and tell it to execute the command that it tells, I guess?
So what is undo? How would you model undo, by the way?
Oh, you'd have to change the initial command to have a negative movement, I guess.
Okay, negative. Okay, good. Yeah.
Since the command object like encapsulates your parameters, couldn't you have the undo method be a member of the same command object, and then it would know what the undo is?
Right. And then redo would do what? What would?
Redo would just do the original operation again.
So there's an execute operation which redo will do again and again, and undo will undo it. And here's the history object. When you know this, undo is so simple, right? As it turns out, being a big fan of undo, I've always been frustrated that every new application I've seen, and I've seen a lot being so old, doesn't start off with undo. Undo is the last thing they put in. And as an example, you guys probably haven't, you've seen things matured, but one of the things that's maturing right now is Alexa and Echo. So for instance, the other day I said, Alexa, turn on white lamp. And that's quite a lot to say, and often it gets confused. And I wanted to immediately shut it off, and I said undo. It didn't work. Okay? If they knew command objects and history objects, they would just it's so simple to implement. And sure, you can't undo everything. You can't undo a purchase. Well, you can undo, they probably don't want you to undo a purchase, but you can probably undo a. So this is something people never think of because they think it's too hard to implement. But with undo, with command objects, it's very easy. So I go and submit an undoable command. At submission time, the execute operation is executed immediately. But we'll also execute it later, and we'll also undo it. So now I can have something like this, an undoable get command, which when I execute, it goes and does a get. And whatever get returned, it stores in an instance variable so that I can negate it later. Okay, so the undo will go and put it. So the undo of a put will do a get, and an undo of a get will do a put. And it just captures so well that I can have a generic undoer that is not tied to anything, that I can use for Alexa, I can use for Word, I can use for anything. And actually, those of you who use object editor, I do have such an undoer that I can use for any object. Okay, and then you can little redo also. Okay, so that's command objects. Okay, object that represents a command, which means an operation plus args. It's a method call. Okay, provides a parameterless execute method. It can call it many things, depending. Okay, to invoke the command, it may or may not return a value. That's a detail. Can have a constructor to take invocation parameters. So somebody who submits the command wishes invocation of the command only in the future or also in the future by the same thread or a different thread, but is something that represents the future. Okay? And the service that executes it is oblivious to what the command does. So there is some service being used, whether it's an undoer service, whether it's a thread pool, whether it's a thread creator, whether it's a parser. None of them quite know what's going on underneath. Okay? And may provide additional methods such as undo. And if you looked at the command objects in NIO, it's got an initiate method, which is an extra method that's called. Okay. And what kind of services can use it? A thread object starts a new thread, a thread pool, an undoer service, parser. Okay? I thought I changed the order here. Okay. Now, going back to say undo and a lot of other examples, I use the word factory and singleton. And anybody want to define what a factory is? Yeah. Yeah.
This is like a class you can use to create objects
Okay. A class you can create to create objects
of a certain type.
of a certain type, meaning certain class, certain interface, or both. Yeah.
Yeah, so you're calling methods to create objects instead of a constructor.
So you don't call constructor. That's the key. And you get an object. Okay? Now you guys both use the word create. I said you get objects without using constructors. So can you see why I'm being a little bit more careful? Yeah.
Well, in your case, you're using stuff like set factory to kind of parameterize the factory and say, hey, you're making a connect command. I'm going to tell you to make the connect command this way. So anytime I call it in the future, you'll know that once I get the single pin and call the generalized.
Okay, yeah, right. So I'm using a factory, and I'm not using constructor, so that's good. In singleton, what's a singleton?
Singleton is just like a single object associated with the class. So it'll,
Okay, so the class has,
yeah,
okay.
the NIO manager like get singleton will just be like the single NIO manager.
Okay, and so,
Anywhere in your code you want to get.
so how would you define a singleton class then?
There's only ever allowed to be one instance of that.
Only one instance of it. Can you use a factory to get a singleton object? Often you do. Now you can see why I said that the factory doesn't create an object. It can just return to you the same object again and again. So you didn't construct it, you didn't call the constructor, the factory goes and gives you an object. It may create an object, new object, or it might give you the previous object. That's the factory. Okay? So we see both concepts in NIO Manager. They exist in NIO also. They exist in sockets. So they're actually used in, exist in RMI underneath. So this is a very pervasive pattern used in distributed computing, of course, and in many other situations. Okay? So, and is a factory a class or is it an object itself? Does it have static methods or does it have instance methods?
Static.
Static? Anybody for instance? When you guys were setting factories, you were setting objects, instances. So whether it's instance or static, that's a separate issue. So it can have static methods or instance methods, depending on whether, with instance methods, if you're going to set factories, then you need them to be instance methods, because then you're saying that I can have more than one factory if I'm setting a factory somewhere. So factory selector, how would you define it? So what's a factory selector? The name factory selector or factory or abstract factory, what would that be? You know, recursion is always wonderful in computer science. Bootstrapping and recursion. I mean, you can imagine in the world there are cars and there are factories that produce cars. And what else can you have if you just apply recursion there? Factories that produce or give you factories. Right? So levels of indirection. Again, indirection is a very powerful tool. And whenever you're stuck with a problem, see whether an indirection will solve it. Okay? So it's a factory to return a factory. So when you were setting, when you're setting a factory in the project, you're using a factory selector, telling the factory selector use this factory to create this object. Okay? So singleton class we've seen. So factory class provides a static or instance method to return an object of some class bound to the factory. Okay, so the factory is associated with a certain class. And so factories are good. So why do we use indirection for factories? Why have factories? I mean, we don't want to use indirection just for the sake of using indirection. It supports singletons. Excellent. That's one reason. But do we want factories for non-singleton classes also? And the reason would be?
We are producing like a very similar object every time, so we don't just need to create a new object. We just need we know it's already pre-configured and we can just generate that quickly.
So configuration is decided by the arguments, right? So what happens is what used to be constructor arguments become arguments to the method you call on the factory. So you supply the same information, you just don't choose a class. So somehow not choosing the class is to your benefit. Yeah.
You have a factory that makes an interface type and then you can decide which subclass to use.
Or which alternative class. They don't have to. Two classes that implement the same interface don't have to have a hierarchy.
Right, yeah, it's another thing.
Right. So we can have alternative implementations. That's why we have interfaces, right? And fine, we have interfaces, we can change things, but how do we exactly change things? We don't want to go and change a lot of code that uses it, so we just go and change a factory. We can change either what the factory returns or change the factory itself. Okay, so we can either make changes to the factory saying don't make this kind of class, now use this kind of class, or we can have multiple factories simultaneously around and a factory selector chooses a particular factory which chooses a particular class. Either way, the user is expecting an interface and they say give me any implementation of a car, okay, and anything that has the interface car, and then they get this kind of car or that kind of car. Okay, so used for singletons and selecting some implementation of an interface, okay, where the user is oblivious to what that interface is or what that class is. Okay, and a factory can be retrieved from factory to choose an implementation of an interface. And a singleton is a class with only one instance, and a factory for that class would return that instance and can be used to enforce singletons. Okay? And whether the factory class has static methods or the factory class itself could be a singleton. Okay, so there can be only one instance of the factory class because again the factory itself is a class. So often factory classes are singletons. Okay? Questions? Okay. What have we seen in these last 4 lectures apparently? Okay, on these background concepts. So we've seen some single thread concepts. Okay, we've seen observer pattern, callbacks, upcalls, MVC built on this. Okay, at least my version of MVC, where the model is an observable that notifies its new use rather than the controller doing so. In the web-based MVC. By the way, if I ever ask you, and I don't think I will, but if I ever ask you an exam question on MVC, I mean the Smalltalk MVC. Okay, which is something one can argue for. Then we saw multi-thread concepts that take the concepts of notification that are in some of the single thread concepts and apply it to multiple threads. Again, in both cases, we're talking of creating big programs from smaller parts, and the smaller parts being loosely coupled. Okay, and then in this multi-thread concepts, we saw the relationship between interrupts, device registers, producer-consumer problem, blocking queues, synchronized methods, wait notify, all good stuff to know. Okay, disabling and enabling of interrupt posting, disabling of interrupt processing, and then we looked at command objects, which, as we saw, are necessary for creating threads, but do many more things too. Okay, and we looked at factories and singletons, which are related in that often the things we use in distributed and concurrent programming require factories and singletons. Okay, and they're also design patterns. Okay, and you've also seen the composite design pattern here. So it's important for you guys to know design patterns. And when you guys go for your interviews, please keep a list of all the design patterns you know. And because people will be impressed by the fact that you know these patterns. Because ultimately you want to create big, good software engineers also want to do things fast and correctly, but also do it modularly.